Good morning, everyone. Kindly turn off your cell phones and maintain silence. I hope everyone is settled. Greetings, distinguished guests, esteemed scholars, and enthusiastic connoisseurs of aerospace sector. With the gracious blessings of Honorable Founder President Dr. Ashok K. Chauhan sir, and under the kind guidance of Honorable Vice Chancellor Dr. Balwinder Shukla ma'am, it is with profound privilege and immense enthusiasm that I extend my heartfelt welcome to the second International Conference on Modern Advancement in Aerospace Engineering. This prestigious gathering, orchestrated by the Amity Institute of Aerospace Engineering at Amity University, Uttar Pradesh, marks an extraordinary juncture where we convene to delve into the cutting edge realms of aerospace innovation. In our collaborative pursuit of knowledge, we are poised to catalyze a future that is not only more sustainable but also replete with the groundbreaking achievements in the domain of aerospace engineering. Today, we embark on a transformative odyssey, forging a global community dedicated to pushing the boundaries of modern aerospace. To inaugurate our event, we will initiate with the customary ceremonial lighting of the lamp. I humbly invite the esteemed dignitaries on the stage to come forward and partake in the symbolic gesture on behalf of this distinguished assembly. कर दिया है। I humbly invite the esteemed dignitaries on stage to partake in this symbolic gesture of lighting of the lamp. Saraswati Vandana, a timeless invocation to the goddess of knowledge Saraswati, will be graced with the melodious voices and graceful performances of the talented students. I request all the students to start with the Saraswati Vandana.
हे शारदे माँ हे शारदे माँ अज्ञानता से हमें प्यार दे माँ हे शारदे माँ हे शारदे माँ अज्ञानता से हमें तार दे माँ तू स्वर्ग की देवी संगीत तुझसे हर शब्द तेरा है हर गीत तुझसे तू स्वर की देवी है संगीत तुझसे हर शब्द तेरा है हर गीत तुझसे हम हैं अकेले हम हैं अधूरे तेरी शरण में हमें प्यार दे माँ हे शारदे माँ हे शारदे माँ अज्ञानता से हमें तार दे माँ मुनियों ने समझी है गुणियों ने जानी वेदों की भाषा पुराणों की वाणी मुनियों ने समझी है गुणियों ने जानी वेदों की भाषा पुराणों की वाणी हम भी तो समझे हम भी तो जाने विद्या का हमको अधिकार दे माँ हे शारदे माँ हे शारदे माँ अज्ञानता से हमें तार दे माँ हे शारदे माँ हे शारदे माँ अज्ञानता से हमें तार दे माँ
Saraswati Vandana, a sacred ritual, not only pays homage to the source of wisdom but also embodies the spirit of learning and enlightenment that resonates deeply within our academic community. Thank you, Shreyashri, Lisa, Tanushka, Lapakshi, and Mansi, for creating such a divine atmosphere. Okay, sir. With the gracious blessings of Honorable Founder President Dr. Ashok K. Chauhan sir and Honorable Vice Chancellor ma'am, Dr. Balwinder Shukla ma'am, we would like to begin with the felicitation. I would like to request Dr. Professor Balwinder Shukla ma'am and Dr. William Silvamurthy sir to kindly felicitate our chief guest, Padma Shri 2015, Dr. Prahlada Ramarao sir. Okay, I would like to request Professor Dr. Balwinder Shukla ma'am and Dr. William Silvamurthy sir to kindly felicitate our chief guest, Padma Shri 2015, Dr. Prahlada Ramarao sir. I would like to request Professor Dr. Balwinder Shukla ma'am and Dr. Silvamurthy sir to finally felicitate our guest of honor, Dr. Andrew Uy sir from the University of Melbourne, Australia. I would like to request Dr. Sanjay Singh sir and Dr. Rajesh Kumar Saluja sir to kindly felicitate our honorable VC ma'am, Dr. Balwinder Shukla. I would like to request Dr. Sanjay Singh sir and Dr. Rajesh Kumar Saluja sir to kindly felicitate our honorable Dr. William Silvamurthy sir. Thank you to all the students for coordinating in felicitation ceremony. No work can attain the status of masterpiece without proper guidance. We at the Amity Institute of Aerospace Engineering are privileged to have Dr. Sanjay Singh sir as the head of institution and conference chair for MIAE 2023. Sir is an alumnus of IIT Kanpur, and his leadership as head of the Amity Institution has been instrumental in guiding our institution towards excellence in education. We believe that his words of wisdom and encouragement would greatly inspire our conference attendees, motivating them to strive for excellence in their respective endeavor.
A very good morning to Honorable Founder President Sir, respected Vice Chancellor Madam, President, Steve, our esteemed dignitaries, guests, guest of honor, keynote speakers, faculty members, and students. First of all, On behalf of Honorable Founder President Sir Dr. Ashok Chauhan, Honorable Chancellor Sir Dr. Atul Chauhan, Honorable Vice Chancellor Madam, Professor Dr. Balvinder Shukla, and all members of Amity family, I feel extremely honored and privileged to extend a very warm welcome to our Chief Guest Dr. Pallada Ramarao Padma Shri 2015, Pro Vice Chancellor S. Vyasa, Director Center of Energy Research, former scientist and Chief Controller R&D DRDO. Guest of honor Professor Andrew, Associate Dean, Student Engagement, Faculty of Engineering and Information Technology, University of Melbourne, Australia, and all the keynote speakers, guests, delegates, faculty members, and students in the second international conference on modern research in aerospace engineering 2023. The theme of the conference is promoting innovation and research in aerospace engineering for self-reliance. It is a matter of great pride and honor for Amity Institute of Aerospace Engineering to organize International Conference MRA 2023, bringing a common platform for scientists, academicians, and students. The main objective of this conference is to instill the research and innovation spirit in the students and community in general, to promote research and innovation in our nation and create researchers of tomorrow. This conference is going to bring together scientists, researchers, academicians around the globe for deliberation and experience sharing. Potential researchers and students shall be able to get technical guidance as well as support through the special sessions by keynote and invited speakers, guests during the conference. We strongly believe that the two-day event will be highly engaging and captivating for all of us. This conference is organized under the visionary leadership of our most respected Honorable Founder President Sir Dr. Ashok Chauhan, Chancellor Sir Dr. Atul Chauhan, under the guidance of Dr. Balvinder Shukla, Vice Chancellor Madam, and Dr. Silva Murthy Sir. Our Founder President has taken the education at global map with 12 universities in India, 18 campuses abroad, 28 schools with total number of 200 students, 10,000 faculty members, 5,000 PhD students, and we have 700,000 alumni across the globe. For Dr. Ashok K. Chauhan, Founder President Sir, research and innovation are Janoon and mission. Welcome, we welcome you, sir. Under the dynamic and charismatic leadership of our Honorable Chancellor, Dr. Atul Chauhan sir, Amity has been able to file more than 2,000 patents, out of which 230 patents have been granted. Amity faculty members have published more than 40,000 research papers in reputed journals. We have transferred 25 technologies to the industry. As a result, Amity University has been conferred National Intellectual Property Award by Government of India in 2020 and IP Excellence Award 2022 for filling the significant number of patents and design. Our dynamic Honorable Chancellor Madam, Professor Dr. Balvinder Shukla has taken the Amity to number 1 position among the private universities with NIF ranking of 22, NAC A+ grade and WASC QA international accreditation. Now our university H index is 130. That is the big number for young university. Let's give a big clap to Vice Chancellor Madam. So in this two-day conference MRA 2023, we have 9 keynote speakers and 68 research paper in 10 technical session will be presented by national, international speakers from IITs, NITs, research organizations like DRDO and ISRO. Amity Institute of Aerospace Engineering advocates a knowledge-centric approach to education tailored to meet the evolving demand of industries such as ISRO, DRDO, HAL, NAL, and more. Through our scholarly contribution, Amity has earned recognition as a prominent hub for knowledge, innovation, research, and intellectual endeavors. We invite collaboration to expedite our journey, align with the industry expectations, and contribute to elevating our nation as a global intellectual capital. I believe that Second International Conference on Modern Research in Aerospace Engineering serves as a crucial platform for nurturing intellectual disclosure and enabling the development of creative solutions to address the evolving demands of diverse industry. So we look forward for your valuable synergy through collaboration and meaningful participation in this conference. So with this, once again, a very warm welcome to all the guests, guest of honor, chief guest, vice chancellor, madam, speaker, delegates, students present online and offline. Thank you.
Thank you, sir, for enlightening us about the conference. Dr. William Silvamurthy is a distinguished figure in biomedical research with over 4 decades of expertise. He holds a master's in human physiology from Christian Medical College, Vellore, a PhD from Delhi University, and a DSc from Bangalore. His 40-year tenure at the Defense Research and Development Organization saw significant contribution in nanotechnology, yoga, military psychology, and polar physiology research, benefiting the Okay, so ladies and gentlemen, let us warmly welcome distinguished Dr. William Silvamurthy, sir.
Very good morning to everyone. Good morning. That's great. Honorable Founder President, Dr. Ashok Chauhan ji, who has joined online because he keeps seeing these programs. Every program he finds time, in spite of the busy schedules. We welcome you, Honorable Founder President. Dr. Prahalad, my friend and also your colleague in DRDO for more than 35 years and a friend, continue to be a friend. Now as Pro-Chancellor of S. Vyasa, which is a yoga university in India, which is in Bangalore, and he is the Pro-Chancellor. He is also Padma Shri. And Prahalad has developed a very important missile, Akash missile. How many of you heard Akash missile? Akash missile? What is Akash missile? Yeah, it is surface to air missile. No, surface to air missile, and you can attack any aerial body, whether it's aircraft or UAV or any other aerial vehicles. So he has developed it, and 40,000 crores worth of production value of this one missile. Let's give a big clap to Dr. Prahlad. We are very proud to have him as the chief guest here. And he has also been spearheading the aerospace engineering, missile technologies. He has been heading the lab, Defense Research and Development Lab, deals with the strategic missile Agni, Prithvi, Akash, Nag, Trishul, BrahMos. All this, his signature is there. So we are very fortunate to have him as the chief guest today. And currently he is working on low nuclear energy. You know, all cold fusion. We talk about cold fusion. Fusion of nuclear fusion occurs in sun at a very high energy level. But then can we do that at low energy level? Low energy nuclear reaction. That is the project which he is dealing now. And Amity is collaborating, Dr. Alpana Goyal and the whole team is working. So Amity and SBRs are together under the leadership of Prahlad. We are now working on low energy nuclear fusion. He has developed 6 reactors, mini reactors, using nickel and also palladium. And then he has given also developed that low energy. He is able to increase 1 is to 1.3 ratio. Energy he is able to get. He is now looking at how do we scale up. So with Amity, we are now working together in this. So thank you, Prahalad, for this collaboration, and we hope that this will see the light of the day. And I must also welcome Professor Andrew Woy, and thank you for joining us. And he has been collaborating with Amity, and your presence here will further strengthen our relationship with you, with your institution, and we look forward to work with you. And welcome to this conference and welcome to Amity. Let's welcome Dr. Andrew. Professor Balwinder Shukla, the Vice Chancellor, she has been with the Amity Group for almost 3 decades, right from the beginning, when Dr. Ashok Chauhan, the founder president who has created this whole Amity universe, 12 universities in India. The latest one is in Bangalore. And the 13th is in Andhra Pradesh, which is in Hyderabad. So he was looking for people to head the university, the first university, Noida, Amity University, Uttar Pradesh. And he selected this great person who is driving 40,000 students, almost about 3,500 faculties, 5,000 PhD scholars. And then ranking was also mentioned. We have reached up to 22 NIRF ranking. And also we have filed patents, projects, publications, all this under the leadership of Dr. Balvinder Shukla. Let's clap for our great Vice Chancellor. Dr. Sanjay Singh is a wonderful, quiet worker. Aerospace engineering, he is heading a number of students who are all from aerospace engineering. Just very good. So all of you are from. So clap for your leader, Dr. Sanjay Singh. Dr. Rajesh Saluja, and who has come from NASA, and Sanal Kumar. Dr. Sanal Kumar has come back from NASA after serving there. Now he is with us along with Sanjay Singh, and he is looking at some important domain of fluid dynamics, particularly the cerebral vessels. How will it be affected by these impacts of aerospace environment? Now, students, we are having this aerospace engineering conference at a very opportune time when India is celebrating 75 years of independence. Aerospace has grown exponentially, and we are now in Amrit Kal, looking towards next 25 years. We are having the presidency of G20. So at this opportune time, we are meeting today in this hall to look at where do we go in aerospace engineering. That is why all of you are very important. You aerospace engineers and budding engineers, scientists, technocrats, all of you are going to drive this aerospace engineering at the global level, not only in India. So attend to all this wisdom, expertise, experience shared by all the experts here. So we have, in this 25 years, what have we achieved in aerospace? India has developed Tejas. How many of you know Tejas? Yes? Just one of you get up and say, what is Tejas? Very good. Well, let's clap for him. What's your name? Very good. So light combat aircraft India has developed. A country which could not make a Tata Indica car of our own design, which was making a fourth generation plus fighter aircraft. The light combat means airframe is composite, lightweight, highly maneuverable, so that you can maneuver the aircraft in any directions, at any altitude, pitch, roll. All this is possible. So light combat aircraft, modern avionics, fly-by-wire, digital cockpit, all that what you want to see in 4+ generation fighter aircraft, India has produced. DRDO has produced. Let's give a big clap to DRDO. And now the country has also is producing transport aircraft. You might have heard SARAS, and now we are also making very great strides in transport aircraft, not only fighter aircraft. Now India is already thinking about the 5th generation fighter aircraft and also the medium combat aircraft. So this is your country. This is your country in 75 years. Advanced light helicopter, light combat helicopter, drones of different types for different missions. So, and aero engine, we have been able to develop a Kaveri engine, even though we could not reach the thrust which is required. But we have developed 75 kilonewton thrust. Aero engine has been developed by India, by DRDO. And flight simulators. And we have developed new materials, missiles, Agni, Prithvi, Akash, Nag, Trishul, BrahMos, interceptor missile, ASAT, anti-satellite missile. All this has happened in 75 years. Isn't it a great thing? Let's clap for the country and the scientists and engineers. And also new materials. We are now looking at new materials, composites. We are looking at smart materials. And we are looking at nanomaterials, high temperature materials. So material science and engineering is contributing to aerospace engineering in a big way. Now, recently, artificial intelligence application in aerospace has come in a big way. Right from design, material selection, and also the computational fluid dynamics, in everything can be used AI in all the A to Z of the development of aerospace vehicle, aerospace engineering can be used AI. That's why Amity has set a very major center of excellence in artificial intelligence, thanks to Chancellor Dr. Atul Chauhan, who has invested about 8 crores with Dr. M.K. Datta heading that group. And let's give a big clap to Chancellor Dr. Atul Chauhan for this great investment which Amity has in total cost has been made. Go and visit all that center of excellence. Use them, not only see, but use them. We want to build partnership with all of you. Now, finally, the themes which you are going to deal here, propulsion. See, now we are talking about hypersonic propulsion, 10 Mach, 15 Mach speed at which we want to drive these, whether it's missile or aerial platforms like aircrafts or spacecrafts. So we are now looking at reusable as well as hypersonic vehicles. That is the latest in avionics, hypersonic propulsion. We are also looking at biofuel. Can we blend in the conventional aircraft fuel, biofuel, so that after some time when we don't have the fossil fuel, can we have aircraft flying with the biofuels? So this is an area for research and propulsion. Space, India has done remarkably well, fourth position now in the world. We have made launch vehicles, SLV, ASLV, PSLV, GSLV, the lunar missions. Chandrayaan 3 was the latest one. The Mars orbital mission and the Aditya L1 mission. See, all this 75 years, a young country like India, and so we are very proud. And also Amity has invested hugely in this area. Amity Institute of Aerospace Engineering, that Sanjay heads. Amity Institute of Space Science and Technology. Amity School of Engineering and Technology. Amity Institute of Defense Technology. Amity Institute of Nuclear Science and Technology. All these founder presidents put this, he envisioned it when he started this as a university in 2005. So let's give a big clap to founder. And we have a great visionary and who thought of all this, including Amity Institute of Materials and Devices, Amity Institute of Nanotechnology. Now the final message is, we have created everything. Now for you student, it is for you to harness the potentials of the expertise, wisdom of people sitting here, sitting there, and emerge as world leaders, global leaders in aerospace engineering. Our blessings to you, best wishes to you and to your family. God bless you.
Thank you, sir, for your inspiring words. Professor Dr. Balwinder Shukla is a distinguished figure known for her expertise in academia, research, and administration. With over 3 decades of experience in industry, academia, research, and administration, she holds a M.Tech from IIT Kharagpur and a PhD from Queen's University, UK. Currently serving as Vice Chancellor at Amity University, Uttar Pradesh, she has played a pivotal. Okay. Ladies and gentlemen, let us warmly welcome distinguished Professor Dr. Balwinder Shukla, ma'am.
Very good morning to all of you. Good morning, my dear students. Most respected Honorable Founder President, sir, Honorable Chancellor, the distinguished guest of honor, Professor Andrew Way, the Associate Dean of Faculty of Engineering and Information Technology, University of Melbourne, Australia, our Honorable Chief Guest, Dr. Prahalada Ramarao, Padam Shri, and the Pro Chancellor, S. Vyasa University and Director of Center for Engineering Research, the former distinguished scientist of the DRDO, and we all know his illustrious career and how he has contributed in the nation building. We are truly, truly honored to have you, Professor Prahlada, at Amity University for this conference, Modern Research in Aerospace Engineering, organized by Aerospace Engineering. When I was going through the program schedule and the themes chosen by the organizing team, I would like to congratulate Dr. Sanjay Singh and his team of faculty and the students who really worked very hard to, uh, to make this conference of such a level. For last 2 days, Dr. Sanjay Singh was discussing with me that due to the UP International Expo, where the classes have been made to work from home, students cannot come to the campus. What to do? And now I'm seeing when all of you, it shows the commitment of each of you to first to the learning, knowing more, secondly to your institution, and thirdly to the discipline of aerospace engineering. Because today when we look at our great success of Chandrayaan 3 being the first country, reaching to the South Pole and successfully landing, and then you know which encourages not only the motivated the nation, but I think it has also given a huge recognition to the scientific talent of this country. The mission like Chandrayaan, or even the discipline like aerospace engineering, it is not just one field, rather it has it's a multidisciplinary, multi-technologies, the discipline, and it has the future belongs to multidisciplinarity, whether it's research, whether it's education, or whether finding the solution to any of the problems for the societal benefit, for the nation building. Our Honorable Prime Minister has already announced that during this Amrit Kal of next 27 years or so, um, that how the India can really reach to the level of fully developed self-reliant nation by 2047 on one side, but also how India can become the knowledge economy, the Vishwa Guru, and I think that it's not only that our Prime Minister is a truly visionary, but at the same time who gives all the time confidence that India's rich heritage and culture uh, is class apart, and people should come to India and know and learn that how advanced was the India and how advanced India can be. And you, as a youth of this nation, and the vision of our Honorable Founder President, you know, I remember in 1998, that in one of the address of our Honorable Founder President, very boldly said that India will be the knowledge superpower by 2030. And that's the way that when he came back from Germany and he had the full commitment that how through knowledge research, community engagement and beyond, how we can contribute to the nation building, and that can only happen when you have the partnership with the industry, national international researchers and scientists, and aligning the activities with the societal needs and the aligning with the national priorities. That's how the Amity, when we see that is the number one university, the university which has filed and commercialized largest number of patents, had a very strong network with the scientists and researchers, especially those scientists, the researchers who have immensely contributed, and after superannuating, they have been with Amity. Whether it is in the you take any domain, you will find the highly successful scientists have been with Amity for so many years, and we are truly delighted to have Professor Prasada with us today as the chief guest. And Dr. Prasada, your presence is not only going to only our faculty, but the future leaders, the future researchers and scientists and technologists, because what you have done in during your career, that is extraordinary. And how did you reach to that level? And developing the Akash missile with your team of experts and all, and that even you will share your journey of contribution to the nation. I'm sure that all my students is sitting online as well as sitting here will really be inspired and will learn from you, and they will also make a mission of their life that how to align their career goals with the nation building and with the how to contribute to the scientific and technological community. I'm extremely thankful to Professor Oi for sparing your time and being here at Amity. And we strongly believe for the collaborative research, and I'm sure while you are here, we will be discussing with our faculties from various disciplines, whether it's aerospace engineering or defense technology or nuclear science and technology and mechanical engineering and other space science and technology. There's Amity, except hardcore medicine, we have all the disciplines. So think that how your university and Amity University can uh, collaborate together, which is mutually beneficial to the researchers, scientists, and also which contributes to the respective countries also, how we can really work together. So I will look forward the outcome of this conference. So Professor Prasada, Professor Alpna Goyal, who you have guided and have keen interest, and I requested Dr. Alpna Goyal also to be here because you have been to her institution and will look for your guidance also in nuclear science and technology, the kind of the facilities Dr. Goyal has created, that is not just for the Amity University students, but that is I would say, the national pride that having that kind of center, and it is for the use of the students, researchers, scientists, not only from Indian university or such organizations, but from the other countries also. And we will seek your guidance how we can popularize and promote it for the benefit of the researcher and scientists and youth of this country to taking advantage of such advanced facilities which are created by the Amity University. Though Dr. Goyal keep on conducting many curriculum design workshops, the faculty development, and various certification courses, but I think it has much more scope, and we will be seeking your guidance to popularize. Dr. Sanjay, I want to congratulate you and your entire team. I'm really very happy and proud that it's just the second conference, but the level which you have brought, and it goes to credit goes to your leadership, and the credit goes to your entire team of faculty members. And I'm sure what we have envisioned for Amity Institute of Aerospace Engineering, with your talented, very experienced faculty and your talented students together, you can really realize that vision of Honorable Founder President, Honorable Chancellor. I wish all the success to this conference. I'm sure the outcome which you have envisioned for this conference, you will be able to achieve. Wish you all the best and grand success to this conference. Thank you.
Thank you, ma'am, for your inspiring words. The chief guest for our conference, Dr. Prahlada Ramarao, is well known for his role as the project director for the Mobile Surface to Area Defense Missile System Akash and National Award Padma Shri in 2015. Aerospace Systems was also in charge of extramural research, academic interactions, industry interactions, and intellectual property. Subsequent to his superannuation, he was appointed as Vice Chancellor of Defense Institute of Advanced Technology, Pune, the only defense university in the country. His areas of interest cover aerodynamics, flight controls, guidance, and many other things. He has been the president and chairman of many organizations, fellow INAE, Aeronautical Society Institution of Engineers, AP Academy, Telangana Academy, System Society, Shockwave Society, and IETA, and recipient of a number of associated awards. Currently, he is the Pro Chancellor in S. Vyasa University in Bengaluru and also Director of Center for Energy Leading Research Team in Cold Fusion. He is also the President of IISc Alumni Association. I kindly request Sir to deliver an enlightening and eloquent talk to address our esteemed gathering.
Well, good morning to all of you, especially my young friends here. I'm happy I am come to Amity for addressing a conference after almost maybe 3 decades. And my interest is how to, the young people, especially in the aeronautics field, what is there in their store for them. I want to address that, but then I will be addressing in my keynote address. Right now, I am happy that so many competent faculty members are there to guide the young students, and the administration and management is fully supporting the committee mission. And also, I am happy to meet Dr. Andrew Oy here. Nice to meet him, and I'm sure we'll develop further interactions. And my talk will not be addressing the defense technologies for the community, because that will be a different arena or a different forum. I'll talk about the general technologies in aeronautics and also in aerospace, and how it will be applicable, and what are the opportunities for you to learn and build up your ambition. Okay, so this is what I know. So I will I went through the program. A lot of good papers are there. Very innovative ideas have come out with the young students. I'm sure Professor Sanjay Singh will have a tough time to see that how their eagerness and the challenges are how they are satisfied. See, they want to do many things. How he can satisfy is a big challenge. So I wish all of you, the participants, the faculty members who are behind this, also for Sanjay Singh and his team who have made this happen. It took some time, I know. He was planning last year. So I welcome all of you, and I'm sure when we interact with the keynote, any more questions you have got, I'm ready to clarify. Thank you very much. Ash, all the best.
We want to sincerely thank you, sir, for the valuable inspiration and wise advice you've given us. Our guest of honor, Professor Andrew Uy, is an academic staff member in the Department of Mechanical Engineering at the University of Melbourne, and Associate Dean, Student Engagement in the Faculty of Engineering and Information Technology. Professor Andrew graduated with a B Engineering in 1993 and PhD in 1997 from the University of Melbourne. Prior to his current appointment, Professor Andrew worked at the Center of Turbulence Research (CTR) at NASA Ames, Stanford University, and as a research scientist at the Defense Science and Technology Organization (DSTO). His expertise area is in the computational study of engineering problems involving fluid flow and heat transfer using advanced methods in computational fluid dynamics. He has made significant contributions in many areas that utilizes the CFD technology, from single-phase laminar and turbulent flows to complex flows involving gravity and multiphase phenomena. He is a fellow of the Australian Fluid Mechanics Society. I now extend a gracious invitation to Sir to deliver a captivating address to our esteemed gathering.
Can everyone hear me? Yes. All right, thanks everyone for coming to this talk, and thanks. I want to thank the organizers and MIT University for inviting me here today. Thank you also Sanjay Singh for inviting me. I had a lot of I learned a lot about the aerospace research here from Dr. Salvamoodi's address, and also I would like to thank um, Professor Babinda Shukla and Pralada Romara for a nice exchange just now as well. Thank you very much for inviting me. All right, okay, so I've been asked to say a few words. I have been in India. The last time I was in India was long time ago. My hair was actually black the last time I was in India. So it was like 20 years ago. But since then we've had a lot of PhD students from India to come and do PhD studies at the University of Melbourne. I've learned a lot from them. They've learned fluid mechanics, heat transfer from me, but I've also learned a lot about the Indian culture from my students. All right, Indian food is always very important. I realize, and also all this. I've enjoyed a lot of conversations about Bollywood and Indian actors and actresses and celebrities as well. So I've learned a lot about the Indian culture. I would what I would like to do here is get um, to experience more about the Indian culture, right? And I really enjoyed myself so far here, and with all the experience here, I want to, I guess, experience more about the Indian culture and also learn a lot about the research in fluid mechanics and aerospace research from our students, from the Indian students at MIT universities and also around India as well. I look forward to interacting with all of you. All right, my area is fluid mechanics. I've also dabbled a little bit with artificial intelligence. But what I know about artificial intelligence is that you need real intelligence in order to get the artificial intelligence to work properly. So I look forward to interacting with every one of you here about artificial intelligence, fluid mechanics, and also the general aerospace engineering research in the coming 2 days. Thank you very much. Thanks.
We wish to express our profound appreciation, sir, for the inspiration and sagacious counsel you've shared with us. Amity University, Uttar Pradesh stands as a shining testament to the visionary leadership of its founder president, Dr. Ashok K. Chauhan, sir, whose unwavering commitment to quality education has transformed it into the global center of excellence. Dr. Rajesh Kumar Saluja, sir, the organizing chair of this conference, merits significant acknowledgement for his dedicated efforts that have made this event possible. His visionary leadership and meticulous planning have paved the way for a successful and enriching experience for all participants. Sir's commitment to academic excellence is the driving force behind this conference success. Now, I would like to request Dr. Rajesh Kumar Saluja, sir, professor at Amity Institute of Aerospace Engineering and the organizing chair of MRA 2023, to propose a vote of thanks. Before the vote of thanks, I would like to request Dr. Rajesh Kumar Saluja, sir, and Professor Sanal Kumar, sir, to please felicitate our Honorable Director, sir, of Amity Institute of Aerospace Engineering, Dr. Sanjay Singh, sir. I would like to request Professor V.R. Sanal sir and Dr. Rajesh Kumar Saluja sir to kindly felicitate Honorable Conference Chair Dr. Sanjay Singh sir. I would like to request Dr. Sanjay Singh sir and Dr. Rajesh Kumar Saluja sir to kindly felicitate Honorable Technical Chair Professor V.R. Sanal sir. I would like to request Dr. Sanjay Singh sir and Professor V.R. Sanal sir to kindly felicitate Honorable Organizing Chair Dr. Rajesh Kumar Saluja sir. I would now like to request Dr. Sanjay Singh sir to please proceed with the opening of the souvenirs and conference proceedings. Dr. Rajesh Kumar Saluja, the organizing chair of this conference, merits significant acknowledgement for his dedicated efforts that have made this event possible. Sir's commitment to academic excellence is the driving force behind this conference success. Now, I would like to request Dr. Rajesh Kumar Saluja, sir, professor of Amity Institute of Aerospace Engineering and the organizing chair of MRA 2023, to propose a vote of thanks.
Good morning to one and all. It is my great privilege to propose the vote of thanks for the inaugural ceremony of Modern Research, Second International Conference on Modern Research in Aerospace Engineering. It is my honor to first of all thanks our most respected founder, President Sir, Dr. Ashok K. Chauhan, for his visionary leadership and his blessings. I would also like to thank our dynamic leader, our respected Chancellor Sir, for giving us the opportunity to organize this conference. I would like to express my gratitude towards our Honorable Vice Chancellor Madam for her guidance and support during the conduct of this conference and making this conference a success. And I would like to thank our chief guest, Padam Shri Dr. Prahlada Ramarao, for sparing his valuable time to come and to enlighten us all during this conference. And a very special thanks to Professor Andrew for flying directly from Australia and being the part of this important event. I would also like to thank our most respected director, sir, Dr. Sanjay Singh, sir. He has meticulously planned each and every bit of this conference, and I'm sure that the inclusion of all the papers which has been under his guidance will definitely give the positive outcome of this conference. I would like to thank all the HOIs of various institutes who have graced their presence during this inaugural ceremony. And I would also like to thank the whole organizing committee, including our faculty members from AIAE and the student volunteers. They have worked day and night to make this conference possible. I would also like to thank our sponsors, technical sponsor Springer and academic sponsor, partner Aeronautical Society of India, for being there, for partnering with us in this academic endeavor. I would especially thank the print and media team. I would also thank our staff, Mr. Mehta, Mr. Kamal, and Mr. Manoj, who have been doing very great job. Uh, Also, I would like to welcome all the delegates and thank you all for participating in this conference, sharing your valuable research. Right? And last but not the least, thank you all the great audience for your esteemed presence. Right? Thank you so much.
Thank you, sir. I now request all the delegates to head to F2 lounge for the high tea and students to F2 backside. Please rejoin back for the keynote session at this very venue. Speaker for today is the chief guest of our conference, Dr. Prahlada Ramarao, and he is well known for his role as the project director for Mobile Surface to Air Defense Missile System, Akash, and National Award Padma Shri in 2015. Please, sir, I'd like to request you to deliver your talk.
Okay. High tea is becoming long tea. Yeah, some of you can come forward. Okay, good. Good morning to all of you. It's a very nice thing to meet a aerospace community like this, looking for new solutions, new opportunities, new challenges. So I thought, let me share with you what is there ahead for you in the next maybe 2-3 decades. So I thought I will put together some interesting aspects of various subjects. Of course, I have not touched the non-aerospace application of aerodynamics and electronics, which are having civilian and commercial applications, like radars or like medicine. I am not touching those things. I am only purely within the domain of aerospace. What can be done? Then also defense application I am not touching because it is a little bit sensitive. So that can be a separate presentation. Both space and defense and aerospace and defense, I am touching only what is technology in it. Keep the mic closer to you. Yeah, technology only I am trying to focus. The PPT works? Hello? काम कर रहा है? Oh, I have to only this, huh? इसमें जाएगा आगे, ये नहीं जाएगा. Okay. These two, okay. So, I am now telling the science and technology of aerospace, how it will directly impact our life, everyday life. So, the security, for example, paramilitary security, defense security, geographical security, intellectual property, whatever you take, security of energy, for example, they all are, even today somebody was talking agriculture. Agriculture, you want to protect your agriculture, there is a drone required, that's what we are discussing. So wherever you go, aerospace has a role to play. So it has a role directly to impact the business, the technology, the economy in every field. Similarly, you take scientific progress, you all know Chandrayana has developed so much of interest in the world. Today we are talking about how do you use this technology on the surface of the moon. One of the major questions people are having is, does the moon have helium? Helium-3. This is a big question. If helium is there in the surface of the moon, can we mine it? If you mine it, can you bring it to Earth? Then the whole energy problem gets it totally solved if helium is available. Today we don't have helium. Like that, any scientific progress, aerospace has a role to play. Now comes technology development. I told you, see, though whatever you start, you take, for example, composite materials. When it was made, nobody thought it will be used for a hockey stick, for a table tennis, or for a human organ replacement. So the materials that developed for aerospace have found application everywhere: medicine, healthcare, agriculture, sports, entertainment. I was just telling somebody, the laser, we used in aerospace for navigation. And nobody thought laser can be used for navigation and guidance of missiles and aircraft. So used. So the technology development is got a major role to play in our daily life, whatever goes first time in the aerospace. Then comes economy and employment. See, the business that aerospace is going to develop, even it's if you see, the space is multi-billion-dollar business. Defense is multi-billion-dollar business. Civil application again multi-billion-dollar. So the amount of economy that driven up in the world based on the aerospace technology is very high. And once the economy goes up, automatically the employment. The employability of youth like you in aerospace is very high. So this is how they all things get combined. Now comes next aspect is design. So aerospace, what is the future challenges in design? See, today we are talking in any aerospace vehicle we make, we talk of what is known as a digital twin. That is, if you are designing a drone, first you make a digital model, arrive at the drone parameters, including the detailed design, then see it working, you are satisfied, then you make a hardware, then you keep checking and digital copy and the hardware copy, how they are matching. So the digital twin concept is come out in a big way. You make a rocket motor, you make a drone, you make a missile, you make a airborne radar for a fighter aircraft, you make a digital twin and then validate. So the detailed design will go into packaging the digital twin, digital hardware right in the beginning. Then modeling and simulation, I told you. The CFD, today, CFD experts are saying that tomorrow I will remove the wind tunnel. Wind tunnel is not required. I can definitely show you all aerodynamic predictions using a CFD code properly using a good computer, high power computer, high speed computer. You don't have to go to wind tunnel testing at all. This is the confidence they have built, aerospace people, that without that wind tunnel testing, you can almost go to flight with the help of a good digital model, CFD model, and detailed simulation. This is the level at which we are going to reach. Of course, the wind tunnel people say, no, you can never fly without at least one test. So this fight is going on. But I think both are upgrading their skills and knowledge. Then comes the graphics, video, metaverse, I saw recently on metaverse exposition where he is telling you how you can go have a space flight or how can launch a air to ground missile sitting in your computer room, and you feel it, you are going to launch yourself, you can feel that 3D effect, sound, and how it will fly and how it can be jammed, and if it jams, how you can overcome. So you have a very excellent, he said it's a metaverse based, and it's a very good simulation. Plus also the maintenance, repair and maintenance. If you got an aircraft, you want to repair and maintain, using a metaverse, you can find out exactly how do you repair and maintain, simulate it, check it, then go and do it. So the exact model is available to you. You can feel it. You can almost touch the hardware and see the simulation. Then comes, see, anything you do, we are doing a design, is it safe? Somebody today mentioned me, and that is, I am doing composite material using organic fibers, no chemical fiber. I said, how is it possible? He said, yes, I will give you a green composite based on natural fibers, natural adhesive. It is totally safe and green. So this is the level to which you have come. Tomorrow we are talking aircraft flying with EV, electric vehicles. So that means there is no combustion taking place in the air. Today, one of the biggest pollution is the combustion of the gas turbine engine in the air. Huge amount of carbon dioxide, carbon monoxide, and nitrous oxide being thrown out. Can you avoid it? That is the green technology we have to solve. Now come to innovation. We want to do innovation. This is all of us are looking at innovation in a very deep way. Innovation. It can be small efficiency innovation. I was doing something efficiency. For example, we are generating thrust in a rocket motor. Can I reduce the specific impulse by 1 second so that I get a higher efficiency? See, even 1 second specific impulse improvement in a rocket thrust will make a huge difference. So that is the smallest called incremental innovation. It can be higher productivity. That means, can I make, for example, today HAL has been asked, you are making 100 aircraft per year. I want 200 per year. Same plant, same manpower, you increase the productivity. Instead of 100 aircraft LCA, Tejas per year, I want 200. Can you give in 1 year? See, this is how do you increase productivity? So that is again you have to innovate. How I can increase productivity with the same manpower, same machine, but can I use different techniques? More digital domain I can use, I can do anything. So that is the innovation one has to work. Then comes a game changer. See, for example, people are talking the next aircraft engine may be working on hydrogen-based combustion. No kerosene, no jet fuel. So this is a destructive innovation. That means there is no more. You don't have to go for a fuel. You have to only use hydrogen. So it becomes a very different world when you are all there. You can get an opportunity. You can find a solution which people earlier generation have not even considered. Okay, and actually feature rich. Whatever you do, it has to be the details are so complex. Every feature of the operations can be introduced into the design and in the modeling. Then comes safety. Of course, everybody is worried about safety. Recently, you have seen so many aircraft accidents. The F-35 was lost. F-35 was lost in one of the operations. Everybody is surprised. F-35 is one of the safest fighter aircraft designed. How can it be lost? The pilot ejected. This is second loss of a F-35. So everybody is worried. Is it safe enough? Then MiG, we know MiG-21 with a continuous safety problem. So tomorrow's design of aircraft has to be extremely safe because nobody wants to lose a life. The value of life is continuously increasing. The human life is becoming more and more precious for everybody in the world. So even one life lost is a huge loss. So the safety has to be very important in your design. Then comes sustained. Whatever you do, can it be sustained? Somebody was telling, I want to go for EV. Okay. Is it sustainable? Can I go for a hydrogen engine? Is it sustainable? The first question is, hydrogen engine, is it sustainable for next 100 years? If it can be sustained for 100 years, you go for hydrogen engine. If you have doubt, be careful. So the sustainability is not 1 year, 5 years. You have to see for maybe generations it has to be sustainable. So people are looking at EV. People still have question: is it sustainable? Wind power, is it sustainable? Similarly, hydrogen-based combustion engine for aircraft, is it sustainable? This is what is the question being asked. Then comes voice command. Tomorrow you will hardly see anything on the keyboard. You have to only give instructions, receive instructions. You tell the computer, you tell the drone, you go to a higher altitude, it will go. You don't have to key in any parameters. You want a aircraft, you will tell voice instruction, go to target number 25, location so and so. If not successful, change over to target number 27. You can give voice command. The system will follow your voice and do exactly what you want. The tomorrow's missions will be, most of them, even military missions or civilian missions will be voice commanded. Today, most of the time the aircraft is flying on automatic. There is no pilot. Pilot is coming along with you, having a beer with you, and go back. So it is not. It's not really. You have to key in any commands. It has to be voice command. This is going to come because you will use all lots of voice commands. And in fact, I own my own, for example, I hardly key in anything. I give voice instruction, voice command, dictate my notes, can see the digital voice to text, you see it and then send it. Very little I am going to type. Then comes out of box solution. Many people are thinking of a lot of interesting solutions. Everything what you think, what you do, see, can I do differently? Somebody was just now telling, I want to make an aircraft which can go underwater, be a torpedo. So out of box, you are flying a small aircraft, and suppose you want to go underwater, can it dive into water, become a torpedo and fly? It is a very surprising that in our Vedic knowledge, that is a few thousand years ago, they talked about a airplane which can go over the water, in the air, under the water. All the three, they said there is one Vimana, aircraft, which can fly in all the three domains. This is what is written in a scripture. We are trying to find out how it was possible. And ergonomics, of course, you all know, it has to be ergonomically attractive. Value should be there, and it should be attractive for you to say, yeah, this is a good product. Now come to materials, because any innovation first start with materials. Whether you got aircraft structure or radar you take, or any warhead you take, the material plays the most important role. You have to understand the material thoroughly, its capabilities, its composition, manufacturing, use, machining, welding, whatever you want to do, you have to understand materials thoroughly if you want to do a product. So it may be metallic material, it may be non-metallic, or it may be composite. It may be anything. And it can also be pure metal, it may be alloys. There are hardly any application where pure metal is of use, except in energy devices. Otherwise, you need only alloys. Then comes non-metal, it can be organic, it can be inorganic materials. Like I told you, composite materials, it can be organic composites, organic fuels. So it can be hard and soft. The new area is coming up in a big way. There is a laboratory in Bangalore. They are doing research in soft materials. What are the future soft materials? Because you will start using more and more soft materials. Whatever you make, it will be more like a real material what you use in your life, like a muscle, like a bone. See, they're all soft materials. People are trying to see how to simulate the materials available in human life, animals, insects, soft material. More and more items will be marketed with soft materials as a base, not directly steels and aluminum. It may be even transplantation. Can we use something which is very close to natural bone structure, or any other structure, skull? It should not be hard like steel. It should be capable of doing the functions, but still it is a soft material. Then comes to technology of smart materials. You use alloys which are working as smart materials. You are also using meta materials for radio frequency applications. For RF communication, RF radars, can I use meta materials? So that is another field emerging. So smart materials, then comes meta materials, then come nano materials. So for example, I am working on nano nickel for energy generation. It's all nano level. And nano composites are also being used for various applications. Okay. Then comes lighter and more durable materials. Then manufacturing process, again, there are so many challenges manufacturing process. It should be lighter, it should be faster, cheaper material, manufacturing process, customized versus see, the mass production will vanish. That will be out of fashion. You don't buy. In fact, you will not buy a car more than will not manufacture a car more than 1,000. Next car will be a different car. So the mass production will vanish and customized production will come. But because of our efficiency in manufacturing, it should be smarter, safer, and greener. Aerodynamics. I am aerodynamics fellow, so I know how aerodynamics change. Especially, you are going to use flexible structures. So it will be flexing like an airship or an aircraft, flexible, but still aerodynamics should work. So, what is the aerodynamics for a flexible vehicle? Then interactive structures. Structures are no more passive, active. And aerodynamics, instrumented aerodynamics, again active. So everything will become active structure, active aerodynamics, active control system. You continued, you want to mimic the way the birds will fly, animals will fly. People are looking at even fish. How can we learn from the way fish is working? Then actuators are embedded in structures, blended aerodynamics, use of metaverse, VL, AR, ML, all your areas. So sensors, we are not good in sensors. We had miniature sensors, upgraded to digital sensor, then smart sensor, intelligent sensors, IoT enabled sensors. This is the future that you are going to work. And system on chip, digital as well as RF systems. Propulsion, I told you, electric propulsion, hydrogen as a fuel, then hydrogen plus electric hybrid as a propulsion. These are all things coming. Space missions, see, one of the most, people are concentrating debris management. Space debris, how do you manage? There is challenges for all of you. You will have to clean up the space to remove the debris. It has to work day and night, sustain, like you have seen. Mars mission will be for 5 years, 10 years. How do you sustain Mars mission? And so new science have to be generated, maybe cosmic energy. You have to tap cosmic energy. So I want to tell you what is ahead for you. Huge challenge. And I thank Amity for this. I would like to go back 50 years so that I can again redo whatever you are doing today. This is what is my dream. And I thank all of you for this chance and wish you all the best. Thank you.
Thank you so much, sir, for such an insightful session. I now request our student Jetlin to proceed with session 2.
Good morning, everyone. Now, I would like to invite the next keynote speaker, Dr. Bhargav Akinapalli, professor from Yangnam University, South Korea. He'll be joining us online this session. Dr. Bhargav received his PhD in Mechanical Engineering, Yangnam University. He received his MTech degree in Aerospace Engineering from JNTUH, India. Currently, he is an international research professor at Yangnam University. His current research focuses on advanced energy storage devices like Li air batteries and the next gen supercapacitor devices. The title for the lecture is Investigation of Thermal Effects on Electrochemical Characteristics of LAZP, anode for rechargeable ion batteries in advanced aerial vehicle systems. Kindly. So now I'm inviting Dr. Bhargav sir. So for the felicitations.
Yeah. So am I audible to you? Okay. So yeah, thank you everyone. Very good afternoon to one and all. And first of all, I would like to thank the organizing committee for inviting me to give the talk on the research which I am currently doing. So my research is on performing advanced research on rechargeable batteries, which can be applied for aerial vehicle systems, which because I'm kind of my specialization is from aerospace and also material chemistry, so I would like to combine both. So because of that, this is the kind of innovative research, advanced rechargeable ion batteries, which can be used in the future vehicles. So these are the contents which I am going to talk about. Research objectives. What are the objectives of the research? Research background. Why? What are the problems? Existing problems currently, and what can be do to solve the problems? And what are the methods I have employed? And what are the results I have achieved? And I will discuss a little bit into the results, and then what are the conclusions I come to. So research objectives, there are four main research objectives. One is to successfully synthesize LZP and LAZP electrodes for lithium-ion batteries. I will talk in detail what are LZP and LAZP in the further slides. And then to apply variable C rates on the capacity of the cells, and to understand how the temperature affects on the batteries. And then finally to apply these batteries in the real life appliances. So research background, application-oriented research background. So we are working on eVTOL, which you already might have known, which is electric vertical takeoff and landing vehicles. When we put batteries into the eVTOL vehicles, as during takeoff, the energy it required is very high, and then while going to the cruise stage, the energy can be limited. Like we no need of huge amounts of energy required during the cruise stage of the vehicle, and then during landing. So takeoff and landing, we need huge amounts of energy to progress the vehicle without any unwanted disturbances. So you can see on this plot, discharge capacity plot, during takeoff, the voltage required is huge. And then as it is progressing towards the cruise, the required discharge capacity is getting high. That means we need more discharge capacity for the battery to run perfectly. And then during landing, it needs the highest amount of the available discharge capacity. And you see there are many lines here, which are the number of cycles. What are the cycles? Which is takeoff, cruise, landing. Again, takeoff, cruise, landing. So this one set is called one cycle. So as we are running more cycles, the overall available voltage for the battery is also getting reduced. So you can see that here. So that is one of the problems we need to solve it. One of the key problems we need to solve it in the battery research. Because as we are charging and discharging the battery, the overall available capacity in the battery is getting reduced. So that means we cannot use complete energy of the battery. So we need to make a limit there. So we should not go below the available discharge capacity. And one more important problem we are facing is the temperature effect. So you can see as we are increasing the number of cycles, the maximum temperature is also raising. So that is unwanted situation. As the temperature of the battery increases, it is a cyclic loop. It falls into the cyclic loop. As temperature increases, the discharge capacity goes down, and discharge capacity goes down, and again raises the temperature. So it is a cycle. So we don't want this unwanted cycle. So that is also one of the problems we need to solve it. And the other thing is work is the solar powered UAVs. So you can see here, as I said already, during takeoff and landing, high energy consumption are required during takeoff and while climbing. And during cruise, the energy might not be as high as takeoff and climb, but that is also huge energy required. So we need to have sustained battery capacity to run it. Even though it's a solar powered vehicle, we are trying to make a backup so that the vehicle can fly even during clouds. So we need a continuous supply of the power. And other thing is the power source oriented research background. That means research the material battery material research. So until now I have talked about where we are applying application oriented research background. Now I am talking about the battery material research, where we are lacking. So all of you having the batteries, which is your mobile phones are having batteries. So all of the batteries in your mobile phones contains this material called cobalt. So lithium, nickel, manganese, cobalt oxide is the material in your mobile phone batteries. Not just mobile phone batteries, all the batteries available in the market are having these lithium, nickel, manganese, cobalt oxide. So the problem with this material is that as we are increasing the temperature, there is huge drop in the capacity. So why I'm talking about the temperature effect, because the earth is not having the constant temperature all around. So if you go to Canada or South Pole or the North Pole, the temperature varies drastically, and if you come to the equator, the temperatures are kind of higher. So when you cannot cover up this whole range of temperature, the battery cannot work like that. So we need different kinds of material which can sustain these kinds of temperature variations. So study of temperature is a key point in the current battery research. And what happens when the temperature increases? So the degradation of the electrode is happening. So that means the material is getting oxidized, and we cannot use the complete available material of lithium. So that is one of the problems. And the second most, and that is the most problem is that 70% of the world's cobalt supply coming from only one country, which is Democratic Republic of Congo, which is in Africa. Because of this not segregated, a concentrated of availability of the source, what happens? The extraction of cobalt needs suitable the conditions which they are extracting is not suitable for humans, but still they are extracting for the money. So that is a geopolitical issue. The world is trying to solve it. So the battery researchers are trying to move away from this cobalt material. And you know what? 50% of the battery cost comes from just cobalt material. So when we can replace cobalt with some other materials, we can also reduce the overall cost of the batteries. So these are the problems which I have found out. So I would like to solve these problems in my research. So what are the methods I have employed to solve these problems? So first thing is I designed one material, lithium zirconium phosphate, LZP and LAZP. LZP is lithium zirconium phosphate and LAZP is lithium aluminum zirconium phosphate. So LAZP is aluminum doped lithium zirconium phosphate. So this material is kind of no one has studied this material as an electrode material. This material is very well known as a solid electrolyte material. But what I have done is, for the first time, I have used this material as a electrode material. So I want to replace the lithium cobalt oxide and other materials, electrode materials, with my material. So this is the synthesis process. I mixed all the source materials and I used mortar pestle for 20 minutes and then sintered for 700 degrees Celsius, and then again used a mortar pestle and then again sintered for 1400 degrees Celsius. So one of the negative sides of this particular material is we need huge temperatures to create this material, stable material. So that is one of the negative points, but we have more positives than the negatives. After obtaining the LZP and LAZP materials, I have used 70-20-10 ratios of activated carbon and PVDF to prepare electrodes. Until now, I have the active material. Now I am preparing the electrodes for the batteries. I have prepared the batteries in a glow box with less than 0.1 ppm of moisture and oxygen. And what are the results I have obtained? So these are the X-ray diffraction plots, XRD plots. So you can see at 20 degrees, there is a peak splitting. Peak have been splitted. So what is specialty of this material is, it is a very highly conductive material, but it is not stable at room temperature. So we need to have stability at the room temperature. So these plots have been taken at room temperature. So even at room temperature, you can see the peak splitting, which confirms the rhombohedral crystal phase, which is very stable. So we can say this material I have synthesized is very stable at room temperature. So what different thing I have done is I have synthesized this material at very high temperature. So because of that high temperature synthesis, I have obtained stability of this material. And I have also taken XPS, X-ray photoelectron spectroscopy, where you can see zirconium 4+ oxidation state, which is very stable phase and very useful for the electrochemical stability. So I think this is kind of pure chemistry. So I'm just skipping out the chemistry part and I'm trying to talk about the general perspective, which we all know. So we all know charge discharge. So this is kind of electrochemistry where we talk about the chemistry of the materials. What happens during charge and discharge processes while we charge our mobile? What happens inside the mobile batteries? So that's what this research is about. That what happens during the charge and discharge process. So you can see the left plot is a EIS plot, which tells us how much resistance the battery is having, battery material is having. So LZP is having low resistance when compared with the LSZP. Sorry, LSZP is having low resistance when compared with LZP. So, and then coming to the second plot, which is cyclic voltammetry, it gives us what kind of oxidation reduction is happening at what voltages oxidation reduction is happening during charge discharge phase. So you might have already listened somewhere or you might have personally faced while charging and discharging your battery, sometimes it explodes or the expansion of batteries takes place. So that expansion is because of this one, some unwanted chemical reaction is happening inside the battery. So we can find out what kinds of oxidation and reduction is happening in this cyclic voltammetry. And next one is charge discharge. So while this is the first discharge, so first discharge also you can see LZP is having high capacity than the LZP material. So that is very good because we can prove that with the doping of aluminum, I have improved LZP into better performing material. And you can see here the D plot, which is various C rates for LZP and LSZP. So what is C rate? For all the people who are having the Samsung mobile, the latest mobile, you might have already seen the fast charging, fast charging and super fast charging. So this C rate tells us this charging rate. So 1C is the regular charging, 2C is the fast charging, and 3C and beyond is super fast charging. So currently I'm working on super fast charging 4C, but I have not presented the results here. So you can see even at 1C and 2C, the battery is performing well. My batteries are performing well. And this is about different charge after different charge discharge cycles. So when you charge your mobile one time, which is approximately 1 day, you might charge your battery, and the whole day you will discharge your battery. That means you will use your mobile, which discharges your battery. So one charge plus discharge gives us one cycle. So I have made my batteries 3,000 cycles. That means I have discharged and charged the batteries 3,000 times. So you can imagine if you charge and discharge your battery one time, here you can say 3,000 days I can charge and discharge the battery. So even after that many cycles, the battery is still performing well. But currently, all the available materials in the market cannot run more than 1,000 cycles. That means it cannot run more than 1,000 days. But my material is still working perfectly even after 3,000 days, specifically in your point of view. And even LZP is performing better than LZP material. And I want to test the temperature effect of the material. So I have prepared a in situ equipment in my lab by my own. I have tested the battery at different temperatures. So I have presented here 2 degrees, 35 degrees and 65 degrees Celsius, but there are also results of minus 40 degrees and also 100 degrees Celsius. So at various temperatures, I have tested the battery at minus 40 degrees, the battery did not even move anything. It did not give any capacity. Even at higher temperatures, which is 80 degrees Celsius, the battery kind of exploded. So I did not put the results here, but yeah, that's the point. So higher temperature beyond 80 degrees, it did not perform. My material specifically did not perform well, and below 2 degrees, it did not give me any capacity. So yeah, so higher temperature, the battery is performing well, even at 65 degrees Celsius. After performing the cycling and discharge thing, I have opened the batteries and checked any anomalies happened in the batteries. So I need to check what are the additional things happening inside the material. I checked XRD after opening the battery. So even after various cycles, 3000 cycles, there are not many impurities I can find out. So that means the battery is the material is still stable even after 3000 cycles. Now coming to interesting part, so which is case one. I have made 3 real-time applications. Case 1, case 2, and case 3. Case 1 is I put my battery to connected the battery to 3 colors, 3 LED colors, red, blue, and green. All the batteries performed well and still continuing to perform at longer times. So yeah, that is one case. And case 2 is I put my batteries in a CMOS setup, which is your PC. So if you remove the CMOS battery, the your computer cannot run. It needs CMOS battery. So I removed the battery and I tested it. So it told me that it cannot run. So the error, CMOS error. I put my battery and tested the. I turned on the PC. It turned on perfectly, and I created a condition here. 1 hour I turn on the computer and put it idle, and then I turn off for 1 hour, which is discharge time. So turn on for 1 hour is kind of charging. So the battery charges when we turn on the PC and discharges when we turn off the PC. So I created a situation where charging and discharging happens here. So I kept 1 hour charging condition constant, but increased the discharge time. So I kept on increasing the discharge time and I put it for 1536 hours. Even after 1536 hours, I turn on the PC turned on well. That means my battery performed very well. And case 3 is that after 3000 charge discharge cycles, I put my cells, I full charge my cycles and full charge the coin cells and then put it aside. And I tested the voltage every day. So you can see as the days are progressing, the voltage existing in the batteries dropping a little bit, and then at certain voltage it became constant. That means as days are progressing, the voltage in the battery kept stable. But in the real-time batteries, which are available in the market cannot have constant voltage after 40 days. But you can see after 40 days my batteries are performing well. It became stable after 40 days. So I can say my batteries might perform well when you apply in a real-time scenarios. So why we are doing this research is I want to put these battery materials in the equipments I have shown you, eVTOL and solar powered UAVs. So the coin cells which I have prepared is not suitable for the UAVs, but we are preparing a pouch cell batteries which can be used to put in the eVTOL and solar powered vehicles, and we are trying to test those vehicles, how the vehicles will perform at different temperatures and different flying conditions. So that is about my research. So what are the conclusions? First thing is that my battery is performing well even at various temperatures. And second thing is, even after various charge discharge cycles, the battery is very stable. So these are the 2 key research points, conclusions which I obtained with my batteries, LZP and LAZP batteries. So this is about my research. So if you have any questions, please.
Thank you so much, sir, for such an informative session. We would now like to proceed with the first technical presentation session.
And when we write the next, sometimes what happens, paper is author is different, but presenting one is different. So you may write the name of the book. Yeah. Online. Sir, if you have any doubts, we have a criteria. Yeah. On each criteria, we have four criteria. Emotional score out of five. Yeah. And that's the calculator. Okay.
A very good afternoon to one and all present here. My name is Madhav Sehgal, and with me here today is Prachi. And we're delighted to welcome you all to our very prestigious second international conference on modern research in aerospace engineering. It would be an understatement to say that it is my honor to be present in company of so many talented and brightest minds across the world. Now, we are about to commence a technical session And I'm pleased to introduce our esteemed session chair, Dr. Andrew Uy. Professor Uy is an academic staff member in the Department of Mechanical Engineering at the University of Melbourne and Associate Dean in the Faculty of Engineering and Information Technology. His expertise area is in the computational study of engineering problems involving fluid flow and heat transfer using computational fluid dynamics. Alongside Dr. Uy, we are our very respected co-chair, sir, Dr. V.R. Sanal Kumar, sir, who has been part of various esteemed organizations and guiding force behind organizations such as NASA and ISRO, and also a guiding force for the students of institutes such as Indian Institutes of Science and our own institution, Amity University, and we thank you for that, sir. He has been our guiding light in the university for years. Professor Sana will be assisting in facilitating the session and ensuring its smooth progression. Now, regarding the technical session dates, presenters will have a total of 15 minutes, with 10 minutes dedicated to the presentation itself, followed by 5 minutes for question and answer session. At 8-minute mark, a warning bell will ring to indicate that there are 2 minutes remaining for your presentation. Now I'd like to introduce a session chair, Dr. Uy, for a few words of wisdom and start the technical session. Thank you, sir.
Okay, thanks everyone for coming. This technical session is titled Aerodynamics, Fluid Dynamics, Wind Tunnel, and Computational Fluid Dynamics. So it's about the general area of fluid mechanics. So as you can all appreciate, this is a very big area in aerospace research and aerodynamics research. So I look forward to seeing what research, all the interesting research has been done in this area. I invite the first speaker now. I believe it's Jayanta Sinha. Jayanta Sinha. And he'll be talking about aerodynamics analysis of the disc shape on the multi-row disc inlet device.
Thank you so much, sir, for your kind words. Now, without any further ado, I would like to invite paper ID 23 with the title Aerodynamic Analysis of the Disc Shape on Multi-Row Disc Inlet Device. And the authors are Jayant Sinha from Amity University, Uttar Pradesh, and Sanjay Singh, sir, from Amity University, Noida.
Organized.
As we are unable to connect with paper number 23, so I would like to invite paper number 27 with the title A Triducted Fan, titling VTOL UAV and Conceptual Design and Aerodynamic Analysis. And the authors are Divij Arora from Lovely Professional University, Sanjeevni Nikam from Lovely Professional University, Riptam Singh from Lovely Professional University, Rahul Kumar from Lovely Professional University, Amit Kumar Thakur from Lovely Professional University, Lovi Rajgupta from Lovely Professional University, and Bijli CM from Lovely Professional University.
Hello.
Yes, sir, can you hear me? Hello.
Hello.
Yes, sir, we are able to hear you.
So, ma'am, I'm sharing my screen now. So good morning, everyone. My name is Divij Arora. I'm from Nagari Professional University. The title of my paper.
Sir, we are unable to hear you.
Just a second. Just a second.
So will it be possible for you to switch on your camera as well?
Just a minute.
Okay.
So good morning, everyone. I am Divij Arora from Lovely Professional University. The topic of my paper is a tri-ducted fan tilting VTOL UAV conceptual design and aerodynamic analysis. So in this paper, we will cover this context in this PPT. First is introduction, materials and methods, airfoil selection process and analysis, wing design analysis, and conclusion. So in introduction, as we know that Wright brothers have successfully tested their initial monitorized flight tests in 1903. Numerous of plane configurations have come up during this period with usual concepts to meet variety of conditions. Fixed wing aircrafts have wings and which are pushed forward by turbine engines or propellers. They are often used by military and commercial applications since they have a greater range and produce a smaller amount of sound while unable to hover in a spot. The takeoff environment affects their flight. The ability of tilt rover unnamed aerial vehicle TRUAV to levitate in place similar to helicopters while traveling at a far greater speeds than a conventional helicopters with aviation mode is its most alluring characteristics. A considerable well insignificance in such UAVs, however, has been observed over past 10 years account of important significant scientific advantages which lower the cost of making novel concepts employing TRUAV. In conclusion, one of the most concepts for combining advantages of fixed wings with helicopter-like abilities, range relevance is tilt rotor aircraft. So basically, this slide says that which materials and methods we have used. The goal is to use a mathematical strategy to adopt the basic rotors and create a collection of designs variations for TRUAVs. Finding ideal circumstances of these types of air vehicles is the aim. So the image you can see in the background, it shows that it's the design which we have done in the SolidWorks, and after this design we have done the analysis that I will show the results later on. The suggestion involves choosing UAV design to simplify the design process and lessen difficulties both on switching approaches. To choose the best design, various configurations are compared using information at hand. The chosen design features a primary surface, a three-duct motor tilt arrangements, along with a normal fixed wing, a V-tail. These configurations include two motors at the wing tips and one on the V-tail. A VTOL UAV is designed in stages, starting with the definition criteria, theoretical design, construction of prototype, and a conceptual text. This process includes a variety of analysis, including UAV analysis and aerofoil analysis. So basically, the first we have just chosen a few airfoils that I mentioned later on in this slides, upcoming slides. So we have done the analysis of that airfoils in XLFR software, and after that, the which airfoil we have chosen. So these are some of the equations that we have used in while analyzing the airfoils, and the type of the mission the aircraft will carry out affects the choice of airfoil, which is crucial component of wing design. The coefficient of lift CL and the coefficient of drag CD, which depends upon dynamic pressure, wing surface, and angle of attack, are two such variables. Additionally, Reynolds number, which are derived from the velocity characteristics, length, and kinematic viscosity, are used to describe UAV's operational range. So yeah, we have chosen NACA 3315, NACA 3618, NACA 4415, NACA 6420, and NACA 6620. These airfoils are analyzed in XLFR 5 at Reynolds number 10 into 105, Mach number 0, and grid 9. So this is the analysis results. Analysis is done in sequence from alpha minus 200 to 200 at 1. Two graphs from given figure A and B are plotted to compare the airfoils CL and CD versus alpha and CL versus alpha. The maximum relative thickness Emax is most crucial factors for the designed aircraft. The wing needs adequate room to house the several motors for tilting. From the above analysis, airfoil NACA 6420 is chosen due to high lift coefficient and its thickness, which is important to house servos for tilting mechanism at the wing tips as shown in the figure. And this table provides various parameters given below, being a perfect balance between having a good amount of thickness and high lift coefficient. The NACA 6420 airfoil further analyzed in the range of Reynolds number between 2 into 105 and 12 into 105. Two graphs figure in last slide are plotted to observe the performance in the variety of values CL versus CD, CL by CD versus alpha, and CL versus alpha. So these graphs tells about the result that we have got from NACA airfoil 6420. Since the airfoil is working fine in the given Reynolds number, it is now further used to make wing model in XLFR 5 analyzed to calculate the coefficient of drag, lift coefficient, and coefficient of lift. But first, wing model is generated in plane. The wing plane design in XLFR 5 generated as shown in figure. XLFR 5 is initially used for quick CL max calculations during wing design process. Throughout, it sacrifices some accuracy due to its speed. To improve accuracy, data from XLFR 5 was validated using ANSYS Fluent, a more powerful CFD program which with the goal of creating CL versus alpha graph to analyze boundary layer behavior at different positions on the wing. The study utilized a meshing approach to discretize the problem efficiency while managing computational resources and employed the SSG omega K model for modeling turbulent flow. Despite high conceptual resource requirements, for efficient surveillance missions, a coefficient airplane configuration was selected with a maximum speed of 35 meters per second. A straight wing was chosen for stability and ease of manufacturing, while a V-tail arrangement was favored for reduced drag and effective control and stability in the hybrid UAV design. The ducted hybrid system enhances lift, reduces energy consumption by enclosing rotor blades in a duct. This design is created using Creo. Parametric software improves two duct fans at the wing tips for vertical mode and tilting for axial motor behavior at the back in a 5-4 configuration and a sub type with upward direct rotors. Velocity inlet. The fluid flow rate and velocity with enters computational area are specified by the inlet boundary conditions. The inlet boundary conditions may need to be time varying depending upon application we have given the velocity 30 meter per second for our model. Pressure outlet. At the borders where fluid exits the computational domain, the outlet boundary conditions define the pressure and flow rate. Pressure boundary conditions may occasionally be replaced outflow boundary conditions. In this case, outlet gauge pressure is kept zero. Vol, the velocity and or temperature.
Sir, we are running out of time. You have to wind up your presentation within 2 minutes.
Sure. So basically, uh, we have kept the temperature at 300 Kelvin, and these are some results that we have got from the ANSYS fluent. So, in the conclusion, I would like to say that this study extensively reviewed a historical, current, and speculative ideas in VTOL technology, showcasing progress in addressing novel challenges and defining concepts. The simulation of NACA 6420 airfoil at varying Reynolds number revealed trends in coefficient of lift and drag, providing valuable insights for TRU-AV design. Thank you.
Thank you for the presentation, sir. Now we'll be starting with the Q&A session.
Sure.
Any questions from the floor? No. Nothing.
If you have any questions, sir.
Okay. Oh,
Hello, Divij. Can you hear me?
Yeah, yes, sir.
It was a good presentation. I want to ask you one question.
Sure,
what
sir.
type of mesh have you used for the simulation?
So, sir, basically, we have used edge sizing meshing and phase meshing in that.
Have you done mesh independent study also?
Yes, sir.
Any other questions?
What was the Mach number range you have used?
We have not gone till the Mach number. This paper only tells about the speed of 30 kilometers per second.
13 kilometers.
Yeah, 30 meters per second.
What was the boundary conditions taken?
So boundary conditions are SST omega, as I have already mentioned in the slide.
That is the model, boundary conditions, sir.
Yeah. So the pressure outlets, outlet gauge pressure was 0, temperature is 300 K, and
Far field boundary conditions or
what? I didn't get.
Far field boundary conditions you are invoked or
No. It's not far field.
Okay. Yeah. Okay, thank you. Over to next question.
All right, that's it. Can you join me thank the speaker again? Thank you.
Thank you, sir. Thank you. You can turn off the camera now. Thank you.
Sir, actually, there is a change. I want to change the name of a person in this presentation.
What change you are recommending?
Sir, there is the name Sanjeevni Nikam. There is a spelling mistake in the name.
Okay, we'll get back to you for that, sir,
Yeah.
after the session. Thank you.
Welcome. Thank you, sir.
Now we'd like to invite our next paper.
So I would like to invite the next paper, that is 39, with the title Parametric Studies of an Unguided Rocket Using Simple Point Mass Trajectory Simulation Model. And the authors are Madhav Banwar from Amity Institute of Defense Technology, Dr. Srinivasa Rao Gurupati, and Manish Kumar Chauhan from Amity University, Noida.
I believe we are facing some technical issues with the presenters of paper number 39. So for now, we'll move ahead with paper number 76.
Yeah, so the paper number 76 is dynamic stall of a pitching airfoil, comparison of open form results with Onera model. And the authors are Rajesh Senthil Kumar, Satvik Thanwagale, Sanjay Ramachandran, Arokriya Fridonal Sherbin Michael, Gegatharan Rajathiranam, and Deepak Lakshmanan from Amity Amrita Vishwa Vidyapitham.
I believe we do have Sanjay Ramachandran in the meeting for paper number 76. So can you hear us?
Yes, sir.
So can you please share your screen and turn on the camera if possible?
Am I audible and visible? For example?
You can start whenever you're ready, sir.
So, yes. Okay, so good afternoon, everyone. Am I audible, right? I can, I mean, okay, so good afternoon, everyone. I am Sanjay and I am here representing my authors, team authors for my topic dynamic style of and pitching in file and comparison of open form cells with the NIRA model. So, in my project, let me talk about the outline of the project. We are doing the firstly after the introduction, I'll talk about the objective of the paper, then the modified Onira dynamic style model, and the simulations that we have performed with the open form, and the results and discussion and conclusion of the project. So, dynamic style is an unsteady force acceleration phenomenon that occurs when any lifting surface is subjected to transient motion when the angle of attack is surpassing the static style angle. This is predominantly seen in helicopter rotor blades and wind turbines, where the angle of attack changes rapidly, and this motion induces a delay in the onset of stall due to the formation of dynamic stall vortices. And the Onira model is the semi-empirical model to predict the dynamic stall, which models the installed and stalled circulations with a set of nonlinear differential equations. So our objective is to simulate the dynamic stall with open form assessment and using the gamma gaseous turbulence model and compare its aerodynamic hysteresis with the modified or linear dynamic stall model. And to study the effect of the reduced frequency and the Reynolds number on the dynamic stall phenomenon and how it affects the aerodynamic performance of the NACA 001 file that we have. So this is the expression for the modified mirror dynamic stall model. Here, the CL is dependent on the airfoil position variables W0 and W1, and the gamma 1 and gamma 2 are the unstalled and stalled lift circulation values. And gamma 1 and gamma 2 are solved with two nonlinear differential equations gamma 1, the different indication for gamma 1 is 20. This is the stall lift circulation expression for gamma 2. This is also dependent on W naught, and the delta Cz is the difference between the linear static aerodynamic coefficient with extrapolated to the extrapolated in the stall regime minus the actual value during the stall. So this is the expression for moment where we have the similar dependencies, and the IM is the correction factor, which have been introduced to quantify the inherent uncertainties due to the semi-empirical nature of the model. Similarly, this is the expression for drag, where we have ID, and this has been used as 1.45. These equations have been solved using the mapping, and have been used for the comparison of the CFD results. So the simulations with the CFD has been performed with KML model. This provides good results for the wall bounded flows, and has provided computationally efficient results for dynamics with a good correlation to the experimental data. So the CFD simulations carried out with Hans model with a moving mesh formulation in open form. This dynamic mesh motion has been solved with interpolating solid body methodology in open form measurement. So this is our domain where we have where we have C grid and six blocks and five patches. The velocity inlet mostly called pressure outlet, and the front and back are the five patches that I said. And these six blocks are divided according to the curvature of the domain. And the airfoil rod is kept as 0.4 meter. The mean angle of the oscillation which we are inducing for the simulation has been kept as the orientation of the airfoil. And firstly, we simulated this we simulated the airfoil for grid convergence to check that the gradients are accurately captured with a static form, making the airfoil static. And we observed that 1,20,000 cells gives a good convergence, and this has been used for the dynamics stall simulations. The simulation type that we use is unsteady as the airfoil is oscillating. And the time step that we use is adaptive maximum current 0.9. These are features that are available in open form in such a way that the maximum current does not exceed the said CFL condition. The time scheme that has been used is a second order scheme, which is time equation 0.5, and the solver used is rope and fulfillment pimple form. For that, the rope and form solves for the compressible cases, and the pimple form is solved for incompressible cases. So these are the cases that we simulated in open form, where the first three cases are to compare the influence of reduced frequency, and the last three cases are to compare the effects of Reynolds number of this for the dynamic stall. So these are our results for the dynamic stall of pitching airfoil, which is induced by the influence by the reduced frequency. This has been simulated for 4 cycles. So one of our objectives was to check whether the simulations of the simulation of the dynamic stall is in line with the literature. So we found that it was in line with the literature as firstly there is an increase in suction pressure, and which strengthens the leading edge vortex as the flow progresses. And we can see the flow reversal that so the airfoil causing the leading edge vortex separation. This happens due to the boundary layer, and we have once the leading edge vortex is separated, this is moved downstream, as and forming the primary dynamic stall vortex. And as that goes across the airfoil, we have the trailing edge vortex formation, which comes from the trailing edge, and this is also shed across the airfoil. And then, as both are said, there's an occurrence of freestyle, where the airfoil after this may come back to the original installed position as the flow readjusts, or it may also be shedding as it is still in the static condition. So these are the results of the aerodynamic hysteresis loops that we have obtained, and a good correlation between.
Sorry to interrupt, sir, but you have just 2 minutes left for your presentation.
Okay. So so these are the results of aerodynamic hysteresis loops, where we have obtained a good correlation between the modified Onira dynamic stall model, the open form results, and the McAllister et al., which is experimental results for the same case. And we have observed a little delay in the stall with the open form results, and as the reduced frequency is increasing, we observed more delay due to the strengthening of the leading edge vortex, and vigorous vortices are shed due to in the case of kappa equal to 0.03. This is our first case, and as it is in the stall region longer than the others. And this is the cases of 4 and 5 which I mentioned, which is solved in simple form, which is compared to the RE equal to 3 into 10 power 6, which is solved using broken form. And the correlation between the open form and the Onira results is decreasing due to the increase of viscous effect, and the viscous effects are not properly modeled with the static pair. So we conclude that the events of the dynamic stall captured with the open form simulations are in accordance with the literature. The delayed onset is observed with the increasing reduced frequency, is supported by both the CFD and the modified Onira model. The open form result, the experimental and the modified Onira model for the first influence of reduced frequency shows a good correlation. And as the Reynolds number is decreasing, in the lower Reynolds number regime, the correlation has been decreased due to increase of viscous effects. The accuracy of the modified Enino model decreases as the Reynolds, as these are not properly modeled with the static data. And further studies in the static data is needed to enrich its prediction, the predictive capability of the modified Enino model in the low Reynolds numbers. So these are our references. Where the first one has been used for the modified domain model, and others have been used in the.
Thank you for the presentation, sir. Your time is up. Now we'll open the stage to the questions.
All right. Yes, I think we've got a question on the.
Hello, can you hear me?
Yeah.
Yeah, can you go back to the slide where you showed CL and CD graph?
Graphs. We are expecting this one, right?
No, not this.
CL,
CD
CL
graph.
and CD.
Yeah.
Break convergence. This one?
Yeah. Here, can you explain me this graph? Because CL is constant, but CD is decreasing.
No, this is related with as increase with the increase of number of cells. So, firstly, we started with some 40,000 cells in the right. This is plotted against 1 by n. So, as the number of cells is increasing, we obtain a closer value to as the number of cells is increasing, the results go constant value in the left hand side. This is how built convergence study is done in here. So as the number of cells increases, the CL and CD approach a constant value, and we can say that the gradients are properly captured with the number of cells that we choose.
And one more question. How did you obtain those lift and drag equations that you have taken? CL and CD.
These correlations these results have been CLCD has been already given with respect to the modified linear dynamical model from our reference. These are all using unsteady aerodynamic relations. So we are using those relations for the comparison of the CFD results.
Yes, you did not invoke the viscosity here. You haven't added the viscosity, but you have used K omega SST turbulence model. How will you correlate?
So this is a separate analytical model. Using this is a semi-empirical model, which uses the potential flow theory equations and also the unsteady aerodynamic equations. And the CFD results are separately where we use the K omega SST. So we from our reference that I mentioned here, the K omega SST results have been found to have a good correlation. Produce computationally effective results for dynamical and correlation matter. So here we observe that K omega SST would be a good provide good results for our CFD simulation, and we compare those CFD simulations results with the results of the CL series EM that I showed you. This is from the modified Onira's dynamics.
So what y plus value have you considered here?
We have considered a y plus value of 5.
What? Y plus value of
5.
5.
Yes, sir.
Is it sufficient to capture the wall bounded flows?
Yeah, sir. I mean, as far as I know, we seen that until y plus of 5, it must not exceed the value of 10 and 13, so that it captures the with the sublayer video.
Okay. Let's see.
What was your angle of attack for getting this dynamic chart?
Yes, sir. So here you can see our mean angle was fixed at 15 degrees and the amplitude of oscillation was kept for 10 degrees. So it goes from 5 degrees to 25 degrees.
Okay, but can you compare with the Onira model?
Yeah, sir. So the Onira model, yeah, this equation we can just give any regime. So now we have given this angle of attack regime for this comparison, and we got this results. So here the Onira cells and the open form cells.
Okay, okay, thank you.
So
thank you for the.
Thank you.
Any more questions from the floor? No? All right, you can join me in thanking the speakers again. Thank you very much. Thank you.
Thank you, sir.
Thank you for the presentation, sir. You can stop sharing your screen. And now we'd like to invite paper number 39 again.
Yeah, so we would like to invite paper number 39 with the title Parametric Studies of an Unguided Rocket Using Simple Point Mass Trajectory Simulation Model. And the authors are Madhav Panwar from Amity Institute of Defense Technology, Dr. Srinivasa Rao Gurupati, and Manish Kumar Chauhan from Amity University, Noida.
The author is just joining the meeting. Please give us just 2 minutes more. Sorry for the inconvenience, everyone. Hello, Mr. Madhav. Can you hear us?
Yes.
Okay, you can share your screen and, if possible, please turn on your camera as well.
Is the screen visible right now?
Yes, it is visible.
Sure. So can I continue with this only?
Yes, please start whenever you're ready.
Okay. So, a very warm greetings to everyone present here. Today, I would be presenting my paper on parametric studies of an unguided rocket using simple point mass trajectory simulation model. For this, the abstract generally contains the idea of the paper that we worked on an unguided rocket system simulations on a MATLAB, making a point mass trajectory model to calculate or to get a comparison among S13T variant of unguided aerial launched rocket system and a grad artillery rocket system, and compare the results for both if we try to convert an grad rocket, which is a land-based artillery system, into an aerial launched delivered aerial delivered rocket launch systems. The keywords are basically unguided rocket system study, etc. During the introduction of this phase, we started to work for a target of 6 degree of freedom model, point mass model, and fluid dynamics model. So the base of this project is made under point mass trajectory model. So for this, we studied various papers from projectile motion using MATLAB by A. Clara and multi-stage 2 degrees of freedom rocket trajectory simulation program by Zachary Daust. So during this paper, we came to know, or we came to find out that many researches were done in earlier days, but recently the work done is very brief, and mostly none of the work is done towards converting a area land-based rocket into an aerial launched rocket system. So this provided us with a insight, and we started our literature review under the methodology of literature review, then working towards aero characterization of a rocket based on engineering methods, semi-empirical methods. Those are all the calculation works that we did on paper. After that, we moved on to the development of a point mass trajectory simulation model, PMTSM model, so to be said. And then we performed parametric studies on various rocket inputs and performed simulations using this PMTSM model via MATLAB. The PMTSM model that we worked used a simple trajectory of a ground launched rocket system and free body diagram for the same. And the equations used for this were four principal equations. Those are x dot is equal to v into cos sine theta, z dot is equal to v into sine theta, theta dot is equal to minus g into cos theta upon velocity, and v dot is equal to thrust minus 0.5 into rho into v square into sref into cd upon total mass minus g sine theta. After understanding the equations behind the point mass, the trajectory simulation model was developed in a mscript mode for in MATLAB, and parametric studies were done using 2D plots as a result. For the simulation work, we inputted some data, as you can see on the screen. These are the input values that we started for the initial case. The open source first case that we made had zero movement, zero initial launch location, 0 points, origin point. The target height was at 0 meters for all the cases, but launch condition was also at 0 meters altitude. The velocity at the time of launch was 0, angle 55 degrees, acceleration due to gravity 9.8, caliber, etc. And the CT factor we have taken is 1.1 for the same. Uh, After the results were taken in, the results were observed in the following four graphs. First was range versus altitude graph of the rocket, starting from 0 meters, and the range we observed was 18,000 kilometers, that is 18 kilometers. That is an acceptable range for the original variant of that rocket, which boasts a range of up to 20 kilometers from launching position. The second graph was theta variation over time. So similarly, the third graph was velocity variation over time and Mach number velocity variation over time. Both are of the same time, but the values are different. One is using Mach, one is using velocity. Once our initial calculations were completed successfully, we moved on to parametric studies for a nominal case that we made. And then we made some calculation changes and we performed the same for a number of cases. And we performed a sample of cases where the range and vertex would be most optimum for our considerations. The results you are seeing right now are the same results that were calibrated or calculated during the results of the simulation. And as you can see, at approximately 2000 kilometers and above, we started to get a range of over 7,300 meters. And by 4,000 meters altitude, we were getting a better range. So these were generally at an angle of 10, minus 10 and 10 degree and 0 degree elevation angles at the time of launch. So at 2000 meters, if we are launching a S13 rocket system, which boasts an accuracy of 5 kilometers, and we are launching a grad rocket at the same altitude at the same angle, it is giving us an accuracy of same about 5 kilometers at a range of 4816 meters. It shows that the if we want, we can convert our leftover stock of grad rockets, original grad rockets, into aerial delivered S13 rockets, which can save potentially a lot of money for capital that is invested in rockets, unguided rocket systems, and hence both rockets can be used via land and aerial launch methods. The conclusion of the paper was based on the results that were obtained by the system studies using PMTSM model. And in this conclusion, we concluded that the during parametric studies, GRAD surpassed performance of S13 unguided aerial launched rocket of the same caliber as GRAD, for which, during literature review, maximum range of S13T rocket system was found out to be 4,000 meters, whereas GRAD at the launch altitude of 1,000 meter and 2,000 meters at launch angles of 10 degrees and 0 degrees surpassed 4,000 meter mark, which is the max range of S13T rocket variant. The references were that we used for this paper are here. Some of them are books, some of them are research papers, and there was two sites that we recommended for the references. Thank you. Any
Thank you for
questions?
the presentation, sir. Now we are open to the questions.
Any questions? Yes.
Yeah, there's some kind of issue with it.
Hello, can you hear me?
Yes, you are audible. Please continue.
Yes. Can you go through the graph velocity or Mach number over a time?
Sure.
So in this case, you have calculated Mach number using ideal gas or real gas?
We have taken ideal gas scenario. Mach number has been taken as the formula input for the MATLAB script at the same A upon V.
So,
V
so
upon A.
can you tell me the highest Mach number that it achieved? It's showing
Yeah,
something.
for nominal case that we took from ground, the grad rocket scenario got a Mach number of 2, that is approximately 700 meters per second, and gradually it decreased from that and went averaged at about 1 Mach sonic
Yes.
speed.
How it has suddenly increased? Any
Uh,
specific reason?
During the initial stage, the rocket is in the boost phase. During the boost phase, till the rocket propellant is burned out, the speed is increasing. But after it reaches the boost phase is over and it reaches its peak velocity, it gradually goes down because the rocket is coming back to Earth.
Yes. Okay.
Madhav, how did you estimate the velocity of sound during the trajectory?
So can I open the MATLAB script if I have? I
Yeah,
think.
how did you estimate the velocity of sound?
Uh,
Because you have to calculate the Mach number.
Understood, sir. Uh, okay. Velocity of sound. Structure, mass, caliber. So please give me a moment. I'm just opening the MATLAB script that I have worked on. It has the formula that I have used for it, and I don't think that I've used in the regular formula that is A upon V, and a little bit difference is there.
Is it depend on pressure and density or depends on temperature and?
So we were dependent on pressure and density. We calculated a graph of Mach versus CD. I am sharing the screen again.
Okay. How did you estimate the temperature variation along the trajectory?
Yes, I am showing that part also. I have opened a MATLAB script that I have worked on for this. Please just hold on a moment. Yeah. So we performed a Mach versus CD calculation graph. The calculations we done was based on the AMCP 70680 280. That is in United States document textbook for free stabilizing rockets.
How did you verify your results?
So we verified results via comparing the data that has been given in that table for the AMCP manual, and after in validating our results via the drag calculations and the sample rocket calculations that is given there, we have formulated our own formulas. So for that, M versus CD graph was obtained, and these were the data that we have used for this. And after that, we inputted a function for atmospheric calculations, for which we performed an atmospheric scenario in which we assigned data for the various altitudes, and inputting those calculations in an if else loop, we found out the value of speed of sound, that is A, and then we inputted Mach is equal to A upon V in the main script, and we run it into a while loop to complete the Rangekutta method and get a sample of around 1000 to 1800 cases depending on the scenario we are playing.
Okay, thank you.
Sure, sir.
I just wonder, how did you take into account the shape of the object in
So
your calculation?
for the shape of the object, we have taken into account the initial shape. So we have defined that the lens are like this, that we are using a conical object for a conical nose, along with a nose length of 450 meters, which is given for a grad rocket or a similar rocket. Then we inputted the length of the cylinder and the fins, and then we performed some calculations for calculating the drag variations and the other calculation for the total velocity and performance stability of a rocket. So this is how we calculated the lift values and other values that were incorporated into the M script at the end. Thank you.
Sure, sir. Do we have any other questions? Thank you for the presentation, sir. And with that, we come to the end of technical session 1. And now we'll proceed for lunch and continue with the session after the lunch. So the lunch for the delegates and chair members in F2 launch, and for the students, it's in F2 back area. Thank you, everyone. Thank you, sir.
This profile.
So, Dr. Omprakash, please come here. So, please settle down. Please be seated. So, we have with us Dr. Omprakash. Dear students, so we have with us Dr. Om Prakash, Professor UPES Dehradun. He has done his BTech from Punjab Music College, Chandigarh, MTech in Aerospace Engineering from IIT Kanpur, and PhD in Aerospace Engineering from IIT Bombay. He has published more than 50 research papers in national, international, reputed journals, presented more than 25 papers internationally, nationally, in international national conferences, and he has guided 4 PhD scholars. So we invite Professor Om Prakash to deliver his keynote address. Professor. Yes.
Thank you, Dr. Sanjay Singh, and giving me the opportunity to present. I mean, basically, I will be doing the marketing of my area of research. I mean, my area of specialization research is flight dynamics and control. So, when aircraft is in flight, so how it is going to fly? So, I mean, dynamics is also very important. Okay, and nowadays we have MATLAB software which can easily help you to analyze dynamics. Okay, so you will see a lot of simulation work in my research, and you will see also how Newton's second law is used to derive equations so that we can analyze if how the aircraft is flying. I mean, I can tell you briefly. I have done two-body dynamics simulation of gliding parachute and payload delivery system, and then currently I am working on hybrid airship and how airships can be used to deliver payload. And I mean, I see future UAVs mainly using airships because we have a lot of I mean endurance available. It can remain in air for I mean number of hours, because for aerial vehicles you have to remain in air. If it is on ground, then it becomes ground vehicle. So
वो नहीं लगेगा ना इसमें फर्स्ट वी हैव टू ट्रांसफर इन इधर से निकाल दीजिए बेटा कोई नहीं निकलेगा ना इसका कोई नहीं निकलेगा ये इधर लगा देंगे नहीं लगा मुझे तो वो अपनी पेन ड्राइव में इसमें डाल दो तो पहला को डालो आप बैठ डाउन एंड यू प्लीज कॉल लाइक दिस इधर उनको ठीक है यू वेट next terminal then yes sir yes then
Next, I would like to call upon Permulla Janki Ramalu, who would be joining us online. Dr. Parmulla Janki Ramalu ADMA Science and Technology University, ADMA Utopia, is a highly accomplished professional with an extensive educational background and wealth of expertise in the field of engineering. He holds a postgraduate degree in artificial intelligence and machine learning, AI and ML, a Master of Technology MTech, and Doctor of Philosophy PhD from the prestigious Indian Institute of Technology, Guwahati. With a rich professional history, Dr. Ramulu has served as the former director of the Center of Excellence for Advanced Manufacturing Engineering within the Department of Mechanical Engineering at the School of Mechanical, Chemical and Materials Engineering at ADMA Science and Technology. His diverse qualifications and extensive network of affiliations underscore his commitment to advancing the field of engineering and research. We call upon you, sir.
Hello, good afternoon to all. Is it audible?
Yes, sir, you are audible.
Okay.
Sir, please
I can start, right?
present the screen, like present your screen, slideshow.
Yeah, I think I shared my screen, right?
Sir, the screen is visible. Please do it on slideshow.
Okay, okay. It is already in slideshow manner.
Okay, sir.
Is it okay?
Yes, sir, it's fine.
Okay, thank you. Thank you for the introduction, and dear all dignitaries and co-organizing members and young vision of India and the future, so many viewers from the university, and I am very much glad to meet you all here for the second conference on modern research in aerospace engineering. So today I am going to speak about artificial intelligence and its infusion in the manufacturing sector, how we can enhance the manufacturing productivity aspect, quality aspect, and other many other things. So this is me, Perumala Janikramulu, and recently I acquired PG in AIML from the Purdue University, USA, which is online mode, and MTech I studied in NIFT Ranchi, and PhD from IIT Guwahati. I'm having and holding so many international and national memberships as indicated here. Presently, I am an associate professor and was former director for Center of Excellence for Advanced Manufacturing Engineering in Adama Science and Technology University, Adama, Ethiopia. I am there since 2015 in the same university and still working there. Today, I am going to speak about ASTU. ASTU means Adama Science and Technology University. What is ASTU and how it is looks like, and about myself, what I am, and artificial significance, and AI manufacturing engineering reality. So when it's coming to the partial view of ASTU, it's look like this. It is a wide campus and almost 550 acres land is
Sir,
there.
sorry for disturbing. Sir, slides not changing, sir.
Yeah.
I can see your
changing.
first slides. Yes, sir. Yes, sir. I can see your first slide.
Still.
Yes, sir. Yes, sir.
Now?
Still... No, sir. Yes, sir. Now it's second slide. I can see.
Okay, okay. Now please confirm me, sir. Okay, it's second slide, right?
Yes, sir.
Have you
Right
changed it?
now. No, no, sir. No changing, sir. It's stuck on
Oh,
second
better I
slide.
use. Okay, I think some system lagging. I think. Now it's okay. Third slide.
Yes, sir. Now it's third slide.
Okay. So this is the partial view of Vastu. This is where the main entrance and almost so many laboratories we have, and the intake of the students from per year almost 5,000 students will be there, and total number of students more than 15,000. Now it's came down to some 5,000. So technology only now is incorporated in the university, and our natural science and the social sciences were shifted to some other place. And whereas my contributions towards the professional contributions aspect, most books aspect and invited talks, webinars, conference, publications aspect, I acquired more than 200 publications in the various publications and various journals. And with respect to teaching experience, from the 2004 onwards, I am teaching for UG as well as masters and PhD. I got almost 19 different courses for the UG, and for masters 12 courses and PhD 6 courses. When I was in IIT Guwahati, for the UG 2 courses I have assisted, and for masters 5 courses I have been assisted. So when we are talking about the technology aspect, what is important in the technology aspect? So technology awareness, one has to know how this technology awareness has to be taken care, because technology has a cycle. That cycle shows from the beginning. Okay, need driven expectation. Technology awareness speaks what is the justification we should incorporate this technology. For the justification, you must have the acquisition system, whether it is feasible to that one or not, whether we can incorporate this technology to the existing system or not. If you incorporate this technology in the existing system, what will happen to the further future perspective of the system? So for that, we must know the technology acquisition. So if you know that system, then you can go for the installation of the technology. So with that, you can adapt the technology by which we can promote the technology to the advancement level. What are the drawbacks? What are the advances? And what the incorporating the new ideas into the technology? How we can further enhance the system can be seen in the technology advancement. Then demonetization will take in place once it becomes the abundant technology. So again, this will be this abandonment completely. We cannot demolish this system. Then whatever the drawback existed in the technology, how we can enhance that one, how we can move towards the again need of that expectation, and like that this complete technology taking place. For example, if you see here, time to reach 100 million customers. If you see here, telephone, when it was invented, when it was introduced to the people, it took almost 75 years to reach to the 100 million customers around the globe. Whereas when it's coming to the internet aspect, it took only 7 years period. Whereas Facebook, it took 4 years time, whereas Instagram, it took 2 years of time. And similar manner, if you see here, the another technology which we are talking now, if you see here, Netflix, which was introduced in 1999, when it took almost 3.5 years of time to reach that 1 million of people. Whereas if you see here, in Chat GPT 2022, it has been introduced a year before, it reached only 5 days of time to reach that one. That means now we can estimate how people become advanced, and how they are thinking, and how they are moving towards, and how they are following the technology. So for that, what upcoming engineers has to do, and what their thinking capability, and how they have to use, or how they have to infuse their ideas into the society without without infecting much of the existing system or upgrading the existing system. For that aspect, what we have to do? What is the alternative for that? And how we can achieve such type of new ideas into the society, and how we can incorporate those systems into the existing system. So for example, another thing, okay, this, if it is slide, so you cannot see this one. Anyhow, can you guess this word, which is already given as a long word in the dictionary? To read this one, how much time you may take? So that means our brain work, our neurological system, how it is going to work to read such a long word. So for that, how much time is required? Such time, suppose such type of words are repeatedly coming in a sentence, or it's repeatedly coming in a paragraph, repeatedly coming in a textbook. How we are going to tackle? How much time you have to spend there to read them and to read all the entire spellings of that word? So such things we need to avoid in future, which is already existing now, but still further enhancement may take in place. So anyhow, for any kind of nation, any kind of nation which is highly, especially if you compare, if you consider our country, which is agriculture based, still we are telling India is agriculture based. Of course, it is a fate for us and fortunate for us. So when agriculture based country is coming, your ideas should match. If you are planning to work in the industry in Indian companies, your idea and your target should be agriculture aspect, first primary thing. Later on you can move on to the other technologies, where there are so many other technologies have come now. So agriculture based, how we can move, how you can infuse your idea into the agriculture based, anything which is a manufacturing system, because without manufacturing system, no nation, any nation in the globe will not exist. For example, if you take the Samsung, which is a South Korean based company, 65% of their GDP is covering by the Samsung company. Only one company is covering 65% of that country's GDP. Just imagine, what about our country? Which company is providing such type of GDP for our growth? So just imagine. So we have only few names in the such a high huge population country, like Tata, Reliance, Adani, like that. What about other companies? What is their contributions? So such a way you need to think. So for that aspect, new ideas has to be incorporated and to be implemented in the upcoming generation aspect. For that, artificial intelligence, which is not a new one which we are talking now, but is already existed from the 1950 onwards. Why it is traveling from 1950 onwards? It is reaching towards to the companies now,
Sorry
the
to
real
interrupt
time
you, sir.
application.
Sorry to
Yeah,
interrupt you, sir, but because of the time constraint, please wind up the presentation within 2 to 3 minutes. Thank you.
2 to 3 minutes. Oh, okay. So the historical artificial intelligence, if you take into the consideration, it has been started from 1950 and still it is going on and it will go further. So one has to know what type of concepts should be known to be an artificial intelligence engineer. If you see here, these are the concepts which has to be known before any implementation of your ideas into the AI system, and to implement and to develop the new system into the societal aspect. And other thing is, there are too few important concepts which has to be further fine-tuned for the artificial intelligence aspect. They are machine learning aspect, deep learning aspect, reinforcement learning, robotics, natural language processing, recommended systems, computer vision, and Internet of Things. These all are now existed. They are working well, and they are working for different companies. And the companies, like topmost companies like Airbus, Boeing, they are using these concepts for their better productivity. Where we can use this one, as these are the application part of the AI, where we can further use. And if you take this one,
Thank
AI
you so
grooming
much,
now
sir.
for the exam. Yeah, what happened?
Okay, sir, you can continue.
Okay, okay, okay. Anyhow, I will wind up. Don't worry. Okay. So when it's coming to the manufacturing reality aspect, manufacturing reality aspect. So in the manufacturing industry till now, it has been classified into 4 revolutions, like first industry level 1.0, industry 2.0, industry 3.0, and industry 4.0. When it's coming to the industry 1 and 2, completely related to the mechanical and electrical revolution, whereas sorry, whereas industry 3.0 and industry 4.0, it is talks about computers and information revolutions aspect. That's where the industry 4.0 is completely talking about the artificial intelligence, where the implementation part of this artificial intelligence have come into picture in the industry 4.0, the consideration. So for hierarchical organization aspect, if you see the any industry which is growing and which is developing around the globe, so it will start from the metal processing level, then it will go to the machine or the process level, then it will go to the system level. So this is how the hierarchy of maintenance of the industry and development of that industry. Once the system level has been developed, and one has to know how to analyze the data and how we can incorporate and how we can improve the how we can exaggerate and how we can implement the real-time system into the industry can be seen through these techniques, these models like data interpretation, AIML system, data enabling modeling, a diagnostic and the prognostic models aspect. These models will help us to improve the existing industry or existing product or existing the quality level of the things. And when it's coming to these modern manufacturing system aspect, how the work system has been categorized and how we can combine them to give the output of that product and how it can reach to the workstation level and to the customer's level. Now I'm going to speak. Okay, and when it's coming to the classification, diagnosis, and the prognostic methods aspect, if you see here, when some machining process has taken place, when the machine gives some vibrational aspect, which develops so many parameters, which involves so many parameters in that parameters aspect, if you see the physics based aspect, if you consider, there will be wavelet transformation and Weir propagation model. This how completely Fourier transformation and other mathematical nonlinear combinations will come into picture. Then when once it is identified that physical system, then we will go for the model where we are going to implement. These are the different models already existed. These models will be implemented. Then we can understand what kind of problem, what kind of maintenance is required for that machine, for which these algorithms will be implemented and the problem will be solved. We can estimate how much time it will work without any repair and without any. This is how we can understand how the deep learning concepts will be used for the artificial intelligence aspect. And this is for example, this is the one simple machine which will will use the concepts of vibration, force, current, and temperature. Based on that, we are going to collect the data. This data will be a multi-objective oriented data. This will be a complicated data. This has to be systematically analyzed to understand what is the RUL, means remain using time is left for the given machine, can be computed through your deep learning and machine learning aspect. So this is what the future of the manufacturing applications, where we are going to use this AI and already implemented, and they are going to implement in future for our Indian industries also. And this is how the publication, how they are increasing the year by year. So this how it is reaching towards the publications in that way. And future, we may see the R&D aspect or the business analysis aspect, and in future we are going to see such type of offices with the AI machines which are working without any human intervention. And finally, I would like to say, teamwork is not just about having the right people, but about the right people work together. This is that's what the success of our Amity, I'm guessing here that way. And thank you very much for this opportunity. I must thankful to Professor Sanjay Kumar sir for giving this opportunity and the entire organizing team of this conference. And thank you very much for your kind attention. Thank you all.
Thank you so very much, sir, for such an informative session. Now, I would like to call upon Riyadi to introduce the next speaker. Over to you.
The next speaker for today's session is Dr. Dinesh Bhatia. Dr. Dinesh Bhatia is an accomplished aerospace engineer and brings 7+ years of expertise in aerospace engineering and sustainable technologies. With a strong research and teaching background, he currently works as an assistant professor at the University of Glasgow, Singapore. Dr. Bhatia obtained his PhD in aerodynamics from Kingston University, London, and went on to secure the prestigious Marie Curie Research Fellowship from EU. His proficiency in CFD and environmental technologies has driven pioneering projects including UAV IoT devices for forest fire prevention and wildlife conservation, CFD driven liquid hydrogen storage, and biomemory for aerodynamics. He has received more than funding exceeding 3,20,000 USD from entities like the EU and APNIC Foundation and underscores that his impactful work. Outside of work, Dr. Bhatia is passionate about sustainability and spends his time identifying sustainable travel initiatives in locations around the world. I invite Sir for this keynote session.
Hello, everyone. Can you see me and hear me?
Yes, sir, you're audible and visible.
Okay, thank you. Thank you for the lovely introduction. So I know that we are running short of time today, so
Your presentation isn't visible.
Yeah, I'm just going to share my screen now. Right. Is the presentation visible now?
Yes, sir. Yes, sir.
Okay. Right. So I won't take too much time today. I'm aware that we're running behind time, so I'll be very quick with my presentation. So today's topic actually is the design of a UAV-based system for wildlife monitoring and conservation. We are basically looking at ways of how we can use existing UAV technology and AI to try and improve wildlife monitoring and conservation across the globe. So background, we know that wildlife monitoring is very, very crucial for conserving and analyzing wildlife populations. We know that India is doing a lot of work now in conservation as well in terms of wildlife. So wildlife monitoring is also very useful as it helps us understand the current status of the ecosystems and detects challenges early. Conservation relies on data like population trends, distribution, and movement. So we can understand the effectiveness of the conservation based on obviously the trends of the population and how these wildlife are distributed within the forest, and of course the movement of these animals. So based on this data, we can really understand what kind of wildlife conservation system we need to adapt um, um, based on the data trends. So this is very important for a healthy ecosystem that we are able to maintain a sustainable population. For critically endangered species, we need to monitor very, very small population sizes. So one such example is that of the tiger in India and how the population was struggling about 10 to 15 years back. So very, very important that we actually monitor the population and then we use effective monitoring methods. So obviously an upward population trend indicates that we are undertaking effective conservation. A downward trend indicates that we need to make changes to the conservation method for quick improvements. So why is conservation important? So we know that after the pandemic, more and more information started to come out regarding the human and animal contact. So drastic or alarming population changes results in potential disease outbreaks. And if you see abnormal wildlife movement behavior, it could indicate that there's a problem in the greater ecosystem. So early intervention measures can actually help us contain such diseases or epidemics that are taking place. So the more we come into contact with untouched animals or we venture further and further into the ecosystem, there is a situation where it is possible that we are going to be unearthing more and more diseases. So the prevention of disease spreading to wider range regions and populations is one of the key concerns for any kind of wildlife conservation. And if we are able to conserve the population, we help in maintaining a healthy ecosystem. So, some examples of zoonotic viruses we have seen SARS-CoV-2, avian influenza, Ebola, etc. All are pandemics which have evolved from the forests. So, in the last 40 years or 50 years, Asia has lost 69% of its population of tigers, elephants, pangolins, and rhinos. So, we're looking at ways in which we can actually sustain these populations without resulting in further losses in the animal population. So, wildlife conservation methods involve human observations and field surveys. So, basically, people are there on the ground, physically counting the numbers. You have a look at pug marks of tigers or other animals. You look at their poop, and you try to understand if the health of the animal, etc. So we also make use of camera traps where we are able to monitor the number of animals moving through a specific area. The other method is to use monitoring devices. So in the case of monitoring devices, we actually physically put on a strap onto the animal and try to understand its movement. So unfortunately, with the use of monitoring devices, a lot of animals find it very, very intrusive, and it actually impacts their reproduction rates as well. So they tried using monitoring devices in penguins, and they found out that the moment they use some kind of a clip or a strap on the penguin, their reproduction rates started to drop because they find it very intrusive. So we also have GPS microchipping for poaching. So we basically incorporate or we introduce GPS microchips into, say, for example, rhino horns or elephant tusks. The problem with the GPS microchipping, though, is that once the animal's been killed, the GPS basically you come to know from the GPS that the horn or the tusk is moving to a different location. By that time, it is too late, so it cannot be a preventive measure. It's a measure where things have already taken place. So it's so it's not a very effective measure in that sense. And finally, the last one is visual observation and satellite imagery for wildlife monitoring. Problem with satellite imagery is that it's not live. You get pictures once every 2 or 3 hours. So, for example, if there's a forest fire, by the time the fire has taken place, you still don't have the satellite imagery. So, once you get the image and you realize that there's a fire, it's too late. So, we need to be able to use the advantages of all of these methods, but also try and eliminate their disadvantages. So, all current methods have some form of advantage and some form of disadvantage. So we need a new monitoring and conservation method that eliminates all of the existing shortcomings. So we want a system which is more or less foolproof, or it works concurrently with existing systems. So the authors of we've written a paper on this, have proposed a UAV-based system for wildlife monitoring. So some of the key requirements from the UAV system include we need to be sure that we are not disturbing wildlife, so minimal human interaction. We don't want people on the ground to that level so that we don't disturb the animals. So we can also implement machine learning for species identification, reducing the database size. UAV systems can then be used to actively detect poaching and illegal trade, because UAVs are very flexible. You can fly them very quickly, and you can basically detect some form of poaching or illegal animal trade taking place. UAVs are also very good for early wildfire detection. So we can combine UAV with live sensors on the ground to actually detect wildfires and provide the data back to the forest rangers. The last thing for the UAV system to be effective is that it should be able to monitor remote and inaccessible areas during day and night. So during the day, it is fairly easy to fly UAVs, but in the night, it's a little bit more difficult. So we need to make sure that our UAV system is able to capture all of this data. So we did a pilot study actually. We selected 2 nature reserves. One is the Koina Nature Reserve in Western India. I think a lot of people might know about this place. It's very close to a place called Mahabaleshwar in Maharashtra. So very, very beautiful place, very beautiful nature reserve. And the other nature reserve we actually identified was the Sri Lana National Park in northern Thailand. And the reason why we chose this national park in Thailand is because A, it has a lot of elephants. Secondly, it is roughly on the same latitude as the Koina Nature Reserve. So technically, if two nature reserves are on the same latitude, the weather conditions can be very, very similar, or the type of plantation or the type of growth can be very similar. So we thought that it's best to choose two nature reserves very, very similar to each other in terms of their geographical latitude. So for this, then we did an environmental operational analysis. We looked at some of the key features of each nature reserve, what kind of environment they have. So we identified that, of course, Koina Wildlife Sanctuary is in the Western Ghats, rugged terrain, lots of hilly regions. It's very, 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 very biodiverse with a huge population of Indian leopards. Maybe in some cases they say there are Bengal tigers as well, but we are not sure about that. Very influenced by the monsoon, often very, very heavy monsoon rains in Koina Sanctuary. Accessibility is still very, very poor, very limited road infrastructure. And wildlife monitoring is critical for not only tiger conservation, but also for leopards, elephants, and pangolins, all of which reside in the wildlife sanctuary. In the case of the Sri Lana National Park, again, it's mountainous terrain with a diverse ecosystem, lots of elephants, bears. It also has a tropical climate with distinct wet and dry seasons. It also has a monsoon, but it's not as fierce as the one that is there in Koina. Accessibility is relatively easier. The roads are much better, and there's well-developed tourist facilities. Wildlife monitoring is very, very key for ensuring that we are able to maintain the unique Thai wildlife as well. So, in this case, what we have done is that we know that Koina is a little bit more rugged, so it requires an all-terrain UAV for dense forest monitoring. Sri Lana is more open to a wider range of UAV options. So based on that, we also looked at some other parameters which could be very, very important. Firstly is the average monthly rain. Koina Nature Reserve gets a lot more rain during June to November, or June to you get a lot of rain from the monsoons and the post-monsoon showers. For Sri Lana National Park, you get a lot more rain throughout the year as opposed to one specific period. The other key difference between Koina and Sri Lana is the average wind speed. So again, in the Koina Nature Reserve, the wind speeds pick up during the monsoon, and you end up with wind speeds of up to 30 kilometers per hour. Whereas in Sri Lana, you're more or less stable with a 10 to 12 kilometer wind speed. Temperature-wise, very, very similar, both regions. So you're looking at temperatures ranging from 40 degrees in the day to roughly 10 or 12 degrees in the night. So in that sense, the temperature differences are not that much. So based on this, we looked at some key design considerations for the UAV. It has to be camera-based so that it's non-invasive and is not disruptive. The drone system should be capable of conducting non-invasive wildlife monitoring. So we need to also factor in that there's a lot of dense foliage in these regions. So we should be able to capture a large area of the forest and be able to capture animals from a distance with good image quality. So these are one of the key operational challenges in dense forests. And of course, night detection is very important. So if the forest is very dense, night detection becomes very, very difficult. So we need to incorporate thermal cameras which are able to check out the thermal trace of each of the animal. So thermal imaging aids in fire detection, assessment, and poacher detection. So we are able to tell by the thermal trace whether it's a fire or someone's poaching or doing some kind of illegal arms running in the night. So you can tell by the motion of the people, you can tell the thermal traces. So we should be able to use this system not only for wildlife conservation, but also for smuggling of something like sandalwood or arms in the forest. So Based on this, we identified the key criteria for the UAV. Should be able to operate in level 5 Beaufort number winds. So Beaufort number is the categorization of the wind speed, which roughly equals to about 30 kilometers per hour. So it has to be water resistant because of the monsoon. Operational range between 14 to 40 degrees Celsius, and it should have an ability to detect animal movements in thick canopies and remote regions. And also it should have strong lossless zoom capability. So based on these 5 criteria, we went on to identify conventional or commercial drones which are available in the market. And from that, we identified the DJI Mavic 2 Enterprise. So we are not saying that this is the only solution in the market, but if we were to design a drone, it would have to be something similar to this. So the drone is very compact and portable. You can fold it and you can take it wherever you want. It's got high resolution imaging, 32x digital zoom, and a thermal camera which is able to provide high quality thermal images. It also has very enhanced safety features such as obstacle avoidance. It also has very good mapping systems, so you're basically in a situation where you're able to map the terrain very easily. So it's got versatile payload options. If you want to incorporate further sensors, you want IoT based devices for communication, you can use that. You can incorporate that into the drone itself. So you can also put in spotlights, loudspeakers, beacons, etc. So a wide range of applications which can be obtained using this UAV. So in terms of range, of course, it has a surveillance area of 2 square kilometers. So that is very, very big. So at one specific instance, you're able to surveil 2 square kilometers. And it has a transmission distance of 10 kilometers. So basically, you can be in one of the forest checkpoints and do a surveillance of 2 square kilometers from a distance of 10 kilometers. It can fly for 31 minutes, which is enough to basically surveil probably about 50 square kilometers of area, and it's capable of flying in 10 meters per second headwinds. So this is very important because if you were to fly the UAV in the monsoons, we need to make sure that it's able to withstand high wind speeds. So 10 meters per second roughly works out to about 24 kilometers per hour. So now we have this UAV, which is probably collecting all these images and giving it back to us. So what do we do with them? So we are using machine learning to actually make use of these images to try and enhance wildlife conservation. So images and videos collected from the Mavic 2 Enterprise Edition or any alternative are valuable for training machine learning algorithms to enhance wildlife identification accuracy. So once you have that, you've trained the model, machine learning can aid in real-time detection of the species during the drone-based monitoring. So this can improve efficiency. So once you've trained the model, you're easily able to identify the species. So apart from that, these deep learning techniques that we're using can mitigate and minimize data storage issues. So you don't need like thousands and thousands of images of one area to actually identify the animal. So the moment you've trained the model, you should be able to reduce the number of images you need to accurately detect what animal species it is. So this will actually help in reducing excess data and optimize data management. So because we have reduced this data management and we are using machine learning to actually identify the species, the number of people that you require physically to sit and identify the animal reduces. So you can then reallocate these resources for other kind of conservation methods. So the model can also be trained for identifying weapons, drug consignments, as well as for law enforcement. So you can basically train them with different imagery of weapons and drug consignments, or maybe a sack or bags or something of that sort. So you know that basically someone's transporting something in the forest. We actually did a sample data set on pigeons in our university. Initially, we used a pre-collated data set that's open source and tested the implementation of machine learning for wildlife conservation. So the machine ML model was created and tested with Google Collaboratory, and we used a model called as YOLO V8. So you can see from the images that on the whole, it was able to Hello? Sorry, can you hear me?
Yes, sir, you're audible.
Okay. And is the presentation visible?
Yes, sir, you're visible.
And the presentation?
No, sir, presentation is not. You
Presentation
please share.
Let's go back. Right.
Yes, now it's visible.
Okay. Right. So I was on this slide. So I was saying that if we use a lot number of images to actually try and train the model, we should be able to get reasonable accuracy of our machine learning data set. So based on that, actually, just the final slide is the conclusion. So a UAV wildlife conservation system shows great promise. We need it should be chosen wisely. So just because we have chosen a specific application or specific region doesn't mean that the UAV can be used for every other region as well. So if you were doing a UAV based system in, let's say, Siberia or in Antarctica, you would use a different system or different type of UAV. So we need to tailor the UAV system based on the local geographical conditions. So that's all from my side. That's the end of the presentation. I'm happy to take any questions.
Thank you, sir, for such an informative session. Next, I would like to invite Professor Om Prakash on the stage.
So, I'm starting from the contents, and you'll see there are different types of models, flight dynamic models. So you have now we have to change. No problem. So how to change? So you can share from here. यहाँ से share. Okay. So I'll not take much time. My topic is mathematical modeling of these different types of airships, and these are hybrid airships. So you will see you have kind of, this is a drone airship. Okay, so there are wing and airship together. So you can see how big is the airship Amazon is trying to use, and you have got Boeing, Airbus planning, and they have made these airships for transportation purpose. Okay, and these are different class of aircrafts, regular aircrafts, and you have got airship, you have got parachutes. Now you can use this parachute kind of, you suspend the payload with this airship. So this figure is trying to make this clear. How can you transport something from the airship? And remember, this is a airship with the wing. So, I mean, we have research work going on in this area. You can see different types of controllers are being used: model predictive controller, optimal aerobot trajectory, or trim calculation of trajectories. So a lot of research work is going on in this area. So mainly what do? You write equations of motion of airship. You need the Newton's second law of motion, which is giving us dynamics equation. Then you need whatever wind tunnel test or CFD is being used, that data also is used in this equation of motion. And you need geometry, which aircraft you are trying to use. So you need airship geometry, and there is something like apparent mass you have to calculate, especially for parachute and airship. This is missing in the aircraft. So that's how you get the simulation. Okay. And here there is a comparison, like in aircraft you don't have apparent mass, in parachutes you have apparent mass, in hybrid you have apparent mass. If somebody is trying to use the simulation, then you have to take care of these things. So buoyancy, I mean, primarily you will see in hybrid airship, you have hardly buoyancy in aircraft, and also kind of missing buoyancy in parafoil. I mean, aerodynamic data is everywhere, you can see in the aircraft. So this is kind of comparison you can see. So, I mean, here you got a big, description of the axis system on the aircraft. The main catching point is the center of volume and the CG. So center of the volume is not, CG is not at the center of volume. So this, if you develop single body dynamic model, so this creates a lot of problem. Next slide I will show you. These are the extra terms in airships, where you have, if you take out these terms, you get the aircraft equations. So doing simulation of aircraft is very easy than doing simulation of the airship. So there are very few people doing simulation the airship. You can see the, complexity. Then you got apparent mass. You got so many equations to solve for apparent mass. This is another problem in solving the simulation of airships. So you can imagine how complex is the simulation of airship. And you have got regular equations of motion of the aircraft, which you can use. And remember, all your CL, CD, and pitching moment from CFD wind tunnel, they need to be converted into these equations. So basically, CL alpha you should be able to tell when you are doing the CFD or the wind tunnel test. CL alpha. What is the value of CL alpha? Similarly, CD alpha. So, here I am giving the comparison. So this is two body dynamics model. You can see the payload is here and the airship is here. And here you have to solve in a matrix form. So MATLAB is very good in solving the matrix form. MATLAB is very helpful in solving in matrices. So you can see how complex is the equations to solve. So but this is fun also to solve these equations in MATLAB. So I have understood MIT has purchased MATLAB, very costly software, and at UPS we have also purchased equally costly software. But using these kind of simulations is fun in MATLAB. I am telling you, it in beginning it's become difficult. So you got 2-3 axis system actually sitting here. So you got one axis system here, one axis system here, one axis system here. So how do you marry all these axes? That is mathematics. So finally we get the 9 degree of freedom equations of motion. If you want to turn or yaw or roll, so this is again very helpful in MATLAB. I am telling you, without MATLAB it's very difficult to solve. Okay, and in MATLAB it's very easy. So you can imagine how many parameters we have to take into account when we do the simulations. But again, you enjoy. So this is kind of aerodynamic wind tunnel test data you can include in the simulation. Okay, so this is CL versus alpha, this is CD versus alpha, this is CM versus alpha. So whatever we study in the class, that is going to be useful. So this is how you get the simulation. I mean, you can tell finally at what velocity this vehicle will be moving, at what angle of attack it will be moving, whether it will be doing nose up or nose down. And if you move the elevator, so how much nose up will be or nose down will be the vehicle. So without simulation, you cannot tell if you move the elevator, how high will be the nose or how low will be the nose of the aircraft, unless you do the similar thing in the wind tunnel, which I have hardly seen anybody doing the simulation in the wind tunnel aircraft. So, I mean, these are kind of simulations you get in the, Ford off model or 9 degree of freedom model. So you can tell what is going on with the aircraft when it is in the flight. So, even the turning behavior also you can see how this aircraft is going to turn. So, you can do any kind of study, like you can vary the length of the suspension lines and the payload. And once you have the model ready, PID is the most famous controller to design. So those who, know MATLAB how to use, control toolbox is very, very important. So this is another NDI control system. Here you anybody can use design the controller. Otherwise, without learning control theory, you will not be able to design the controller. So here this NDI control, without learning the control theory, you can design the controller. This is mathematical in nature. So same control system equations you have to you get A matrix, B matrix. Anybody who knows control system will understand how difficult it is. So you get A matrix, B matrix. So I mean if somebody is very good at control theory, you get the transfer functions of each of velocity or angle of attack or pitch rate. So you can find out the transfer functions. And root locus and Bode plot is very, very famous plot in MATLAB you can get. So lot of analysis can be done once your model is ready. Once your model, you can see how much analysis is being done. Sometimes you try to enjoy getting all these simulations. So just for the purpose of showing how much we have. Then bifurcation is another method. You can analyze any dynamic system. So I'll not cover in detail, but this is another software. You can get the graph, and in that graph you will get the eigenvalues. You will get the eigenvalues. If somebody knows what is the eigenvalue, from eigenvalue you can tell the dynamics of the system. So there are multiple ways of getting the eigenvalues. So once you know the eigenvalue of the system, then only you can tell is this system is dynamically stable or dynamically unstable. Very few people work in this area, dynamic stability, I am telling you, and understanding the eigenvalues. So just to tell you, these are the eigenvalues of a hybrid airship. So you got one pitching oscillation and one heave oscillation and one short period phygoid oscillations. So dynamics of the aircraft is very complex, short period phygoid. So here you can tell which motion is stable, which motion is unstable. So this is just towards the end. So you can use a number of degrees of freedom models to do the simulation. Depends on you how complex you can develop the model. And then you can find all the longitudinal dynamics and all the trim conditions. When the aircraft is flying, it is flying in the trim conditions. So what is the velocity of the trim? What is flight path angle at the trim? What is the pitch angle at the trim? So this is the final result what you get. So for hybrid system like airship, CG, center of volume, they are distinct. So there is complexity here, but slowly and slowly you can understand all the things, and maybe somebody will get interested to work in airship area. So we have done some publications on this. And with this, I would like to conclude my presentation. Thank you. I hope there is any question.
Thank you so much, sir, for such an insightful session. Now we would like to proceed with the technical sessions 4 and 5. Technical session 4 will be taking place at F2 Seminar Hall itself, and technical session 5 will be taking place at F1 MDP Hall. Good afternoon, ladies and gentlemen. We are about to commence our technical session 4 by the track name Aerodynamics, Fluid Dynamics, Wind Tunnel, and Computational Fluid Dynamics Airborne Defense Systems. I'm pleased to introduce our esteemed session chair, Professor Andrew Uy of the University of Melbourne and Associate Dean Student Engagement in the Faculty of Engineering and Information Technology. He brings a wealth of knowledge and experience to the said domains, and we are privileged to have him guide through the session. Alongside, we have our capable co-chair, Professor V.R. Sanal Kumar Sir, who will be facilitating in assisting the session and ensuring its smooth progression. I would like to request Honorable Chair Professor Andrew Sir to share a few words to the audience.
Okay, thanks very much for the introduction. I guess I just wanted to say that I've had enjoyed all the presentations so far, and this session proved to be the title is very relevant to the aerospace area on aerodynamics, fluid dynamics, wind tunnel, and computational fluid dynamics airborne defense systems. Right. So I look forward to listening to all the talk in this session. Thank you.
Thank you, sir. I would like to take a moment to share the guidelines for the presentation. Each presenter will have a total of 15 minutes, with 10 minutes dedicated to presentation itself, followed by 5 minutes of question and answer session. You'll hear the bell first at 8 minutes mark and would be stopped at the 10-minute mark. The chair and co-chair will allocate points based on the presentation. Now I'd invite Vedika to proceed with the session.
Good afternoon. The first paper ID which I would like to invite is paper 79, paper ID 79, titled as Conjugate Heat Transfer in 2D Square Cylinder Using Lattice-Boltzmann Method, which is presented by Anif Hussain and Behram Selik. I would like to call them.
Good afternoon to everybody. Am I audible? Good
Sir, you're
afternoon.
audible but not visible.
Okay, let me turn on my camera. Am I visible?
Yes, sir, you're visible.
Okay, let me share my
Sir, your
presentation.
presentation is not visible.
Is it visible now, the presentation?
Yes, sir, your presentation is visible. Sir, please,
Okay.
please inform us when you begin. We'll start the timer then.
Okay, I'll start right away.
Okay, sir.
Good afternoon to everybody. I'm Anif Hussain. I'm currently pursuing MS at Istanbul Technical University in the field of aerospace engineering. I am specializing in computational fluid and heat transfer problems using parallel computing methods under the guidance of my advisor, Dr. Bairam Chelik. So my heartfelt gratitude to the respected faculty members and organizers of this international conference. I would like to welcome the panelists and all the participants to my presentation. Thank you. So the topic of my paper is conjugate heat transfer in a 2D square cylinder using Latz-Boltzmann method. I'll be covering the following topics in today's presentation, hopefully, if the time permits. So starting with the introduction, Latz-Boltzmann method was developed in late 1980s as an alternative tool to solve problems in fluid dynamics. Fluid is modeled as a collection of particles occupying discrete positions in space. The origin of Lattice-Boltzmann method occurred from the lattice gas automaton, which is the combination of kinetic theory of gases and statistical mechanics. The classical Navier-Stokes equations have been able to be derived from the LGA. This provided a scope for fluid simulation using this technique. So the Boltzmann transport equation is the fundamental equation describing the dynamics of gas or a fluid. The collection of particles at discrete locations are represented by a distribution function f. The Boltzmann equation relates this rate of change of distribution function with respect to time and space to a collision operator on the right hand side of equation 1, as you can see. This collision operator is a complex function and it's difficult to solve this partial differential equation analytically. Various approximations for the collision operator have been put forth. The most famous was introduced by Bhatnagar, Gross, and Crook. They used a scalar operator to approximate the collision operator. Latz-Boltzmann method uses this BJK approximation in the Boltzmann transport equation to model flows. The simplified equation is shown in equation number 3. Coming to the discrete form, the discretized form of this equation is derived by Chapman expansion, which gives us equation number 4. As you can see, it's marching both in space as well as time. It's second order accurate in space and time, and it resembles, it's similar to a finite difference expression. However, it has a stability constraint on the ratio of relaxation time and the time step, which should be greater than 0.5. So coming to the advantages of LBM over traditional CFD solvers, the foremost is its inherent structure for parallelization makes it very time efficient. Another key benefit of LBM is that it solves pressure through an equation of state directly, whereas in traditional CFD, we need to solve for pressure at each iteration. Also, the important advantage related to this study is across a heterogeneous domain. In LBM, it simplifies the modeling of heat transfer as the heat flux and the temperature distribution across the different materials or phases is conserved naturally. The algorithm for LBM, in step 1, it involves the discretization of domain uniformly, and we select an appropriate lattice arrangement based on the dimension of our problem. As the dimension of the problem increases, the number of degrees of freedom also increase, and the probable number of direction in which the particle can move also increases. In 1D scenario, we use D1 Q3. For 2D, we employ D2Q9 lattice arrangement, and for 3D, we use D3Q19. These are some of the general. So the first step, it lays the groundwork for subsequent computations depending on the dimension of the problem. The step 2 involves the initialization of macroscopic state variables and the equilibrium distribution function. This step is actually, it sets the initial condition of our simulation. In step 3, we enter the core of LBM process. In collision phase, the interaction between the particles are taken into account and the distribution functions are updated based on BJK approximation. And in the streaming phase, the updated distribution functions are moved to the neighboring lattices based on the velocity direction of each distribution function. The fourth step is applying proper boundary condition. Typically, two types of boundary conditions are encountered in lattice-Boltzmann method: density or pressure-based and velocity-based. These conditions are expressed in terms of unknown distribution populations on the boundary nodes. So it adds a layer of complexity to this process. However, such boundary conditions have already been studied in the past, and instead of deriving them, I have directly used them in this study. Step 5 and 6 involves the recalculation of macroscopic properties and the equilibrium distribution function. These two steps actually interconnect the microscopic scale interaction and the macroscopic behavior of the fluid. And finally, the final step is that we iterate through steps 3 to 6 repeatedly until we reach our desired simulation time. That is, we again do the collision process, the streaming, apply the boundary conditions, and recalculate all these values. Now I can transit into the application phase, focusing on conjugate heat transfer. We are dealing with a heat transfer across a heterogeneous domain, which accounts for conduction within the solid and convection within fluid. Lattice-Boltzmann method is advantageous in this scenario as no additional boundary condition is needed on the solid fluid interface. Otherwise, in traditional CFD, we need a conjugate boundary condition at this solid fluid interface. For our test case, we have chosen a benchmark problem, the flow over a bluff body in a 2D channel. The fluid is initialized to a high temperature. This setup allows us to observe the interaction between heat transfer and diffusion around the square cylinder at a low Reynolds number.
2 minutes left.
To conduct the simulation, we have employed a high-performance computing environment. Both heat and flow solvers have been programmed in CUDA to utilize parallel processing. The blockage ratio is kept as 4, and the grid size is chosen as 600 to times 160 in X and Y directions, and D is the characteristic length 40 lattice units. The momentum boundary conditions are tabulated, as you can see in the table. The channel inlet, we give a fully developed flow, and the channel outlet, an open boundary condition is used, and the top and the bottom walls and rest of the edges, we use no slip. In the thermal boundary conditions, we use at the inlet, we give a thermal starting point of T equal to 1, and the channel outlet and the walls are adiabatic. At the fluid square interface, no additional condition is needed. Now coming to the flow field, in analysis of flow and heat solver results, we utilize ParaView for post-processing. At low Reynolds number, a noteworthy pattern emerges. The flow, after initially separating in the wake, reattaches downstream, indicating a predominantly steady behavior. However, as we approach a critical Reynolds number, a shift occurs. The flow becomes unsteady as the Reynolds number is increased to 60. At this point, phenomena of vortex shedding is witnessed downstream of the flow, and it becomes more prominent as the Reynolds number is increased further. The key observations in the thermal solver, whereas at low Reynolds number, a uniform diffusion of heat occurs towards the rear of the cylinder, giving the cylinder a relatively homogeneous temperature distribution, although the front face has the highest temperature at all cases. As the Reynolds number increases to 50, a transition is observed within the cylinder. The temperature distribution becomes non-uniform. Higher temperature diffusion occurs in the front, and the rear part seems to be affected by the downstream flow behavior. At critical Reynolds number, the vortex shedding seems to impact the rear end of cylinder, which remains at a lower temperature. This implies a cooling mechanism occurring at trailing edge, which is driven by alternating separation and reattachment of the flow. To ensure the accuracy and reliability of our simulations, we validated our results with established data. The comparison of pressure coefficient along the edges of the cylinder with experimental data was made by changing the blockage ratio to 8 and increasing the Reynolds number to 160. It showed a deviation of 2.13%, indicating a close agreement. Similarly, in case of heat transfer, experimental results were not available for Reynolds number less than 160. So we made a comparison with finite volume method
The
of
time is up.
paper. Okay, I have to stop or can I go?
Yeah, now you can start with the question and answer.
Okay, that's it. This is the validation, and finally, it was the conclusion.
Any questions from the floor? I guess I have a question. Why do you put a blockage ratio of 4? Is there a reason you have a blockage ratio of 4?
So actually, the previous my advisor's previous problem was with the circular cylinder, and it was they had chosen the same blockage ratio of 4. So I had to check whether the critical Reynolds number was matching. If I changed the blockage ratio, so I didn't know where the critical Reynolds number would lie. That's why.
Thank you.
In your analysis, you have taken adiabatic assumption for conjugate heat in conjugate heat transfer. Is it correct?
On the walls.
Yeah.
On the channel walls, yes, sir.
Yeah, you are solving the problem for a conjugate heat transfer. Is it correct?
Yes, sir.
Do you have the verification, results verification on that? Did you
So
try with adiabatic wall? Did you try
yes,
with?
sir. Yes, sir. That's where she stopped me the presentation. It was for the second validation case was based on the average local Nusselt number, where that's where I couldn't speak on that.
So it's good. Your agreement, the average Nusselt number and all that is matches with experimental.
Yes, sir. Yes, sir. It's 1.13% deviation, so it's quite close.
All right. Okay. Thank you.
Thank you, sir.
Well, you can show your results now, I guess.
You have to try your problem with the diabetic wall condition.
You can show your results while you answer the question. Anyway, any question from the floor? Anyone else? No more? Well, all right. Okay, if you can join me in thanking the speaker for a good presentation. Thank you.
Thank you, sir. Thanks a lot.
Next, I would like to invite paper ID 83. The title of the paper is A Comparative Study of Dual Throat Nozzle for Fluid Thrust Vectoring Applications, presented by Shiv Sakti M. and Surendra Bogadi. It would be presented online, so you may join. Sir, you may turn on your camera.
So kindly present your slides.
Hope my presentation is visible.
Sir, you're audible and visible.
Thank you.
Sir,
Hello all.
please tell like when you would like to begin. We'll start the timer.
You shall start now.
Okay. Yes, sir, you may start.
Okay. Hello all. This is Shiv Sakti, and the title of my work is Comparative Study of Dual Throat Nozzles for Fluidic Thrust Vectoring Application. And I was guided by Dr. Surendra Bogadi, Associate Professor, Father Lakshmi Engineering College, Chennai. So this is the outline of the motivation for this work, I want to emphasize on one single point. That is that at higher speeds, the conventional, control surfaces are significant in playing their role. But when it comes to lower speeds, the control surfaces are not that efficient, and for that reason, aircraft, real aircraft, that is Harrier jump jet, they are using this control surface. I mean, these flight, thrust vectoring nozzles for, I mean, takeoff and short landings. And this objective of this work is to first, I have started designing a dual throat nozzle without anything, but then I have added an injection, then a BDTN, which is a bypass dual throat nozzle, and that has two types of bypass tech. One is V shape and another one is arc shape. And we have performed the CFD simulation, and we have compared these nozzles for performance parameters like deflection angle, coefficient of thrust, and discharge. And this is introduction to thrust vector control. And as you can see, mainly it is mechanical and fluidic thrust vector control. And out of these, there are many fluidic thrust vector control techniques. Out of which we are focusing, we have focused on this dual throat nozzles. And in the dual throat nozzle, if you add a bypass from this downstream to the throat, we call it as BDTN, that is bypass dual throat nozzle, and it has higher thrust vectoring efficiency and lesser thrust loss when we compare with other fluidic thrust vector nozzles that uses DTN, that is dual throat nozzle. And these are the advantages. As you can see, comparing to mechanical thrust vectoring controls and conventional techniques, these are very simple in structure, lighter, and that there's very pure moving parts. And as I mentioned earlier, it has higher thrust efficiency and no compromise in discharge and minimum thrust loss, and it can perform reasonably good in vectored and non-vector state. And applications are these are used in these aircrafts that are mentioned. And literature survey, we have referred many literature, and out of which I would like to mention this literature by H.T. Kim. He is the one who started using this these type of R type bypass tech. Previously, everyone were using this V type. As you can see by intuition, we can see that this usage of R type bypass will result in lesser pressure loss. And also this starting problem of dual throat nozzle. See, a dual throat nozzle has shock immediate to the throat, and that is also a very strong shock. So, in order to counter this problem, people started using this bypass tech that is connecting this upstream and downstream and after the throat, they are connecting with the bypass tech. So this will result in neglecting the shock, and it moves the shock towards outside the nozzle. So this is the methodology that I have chosen. We are first initially finalizing the nozzle geometry, then we are validating the CFD method, then pre-processing, which involves domain geometry involved, then grid independent study, and we have chosen the turbulence model and boundary conditions. Then after that, we take results from that and we compare. So this is the design drawing of the DTN nozzle. And we have referred many literature, and out of which we took promising parameters like the divergence angle, these length ratios and all. And we have chosen an optimum design. And as you can see, this is a DT nozzle, and we have this bypass included in it. We call it as VBDTN, that is V-shaped bypass dual throat nozzle, and another one is arc shape. And as you can see, the bypass duct diameter is 3.7 mm. That is from literature, it is found that it has to be 0.185 times of the throat diameter. And this is domain boundaries. We have pressure inlet, nozzle wall, then we have pressure out, and we ensure that we have a big domain that is 30 times the diameter of the throat so that we can visualize the flow. And CFD simulations for that we did grid independence analysis, and for this we have chose 3 grids, and you can see from the graph that I have plotted the pressure variation, non-dimensional pressure variation, and it is clear from the graph that the medium mesh and fine mesh are almost same. So we have chosen medium mesh for the present work. So these are the boundary conditions. We have pressure outlet, pressure inlet in IDTN, and we don't have any injection in DTN. So we have the whole nozzle as wall, and in we also have this VDTN. That is the VDTN with arc V-shaped bypass deck, and also the AVDTN, that is arc-shaped bypass deck, and we the present work has simulations for non-dimensional pressure ratios from 2 bars, 4 bars, 6 and 8 bars, and we have used Caves non-turbulence model. And also we have validated the method, and for validation we have chosen this pressure variation along the nozzle, and you can see the trend is same, and it is not exactly matching with the data because we are choosing different nozzles, since but still the variations are matching. And also to reinforce validation, we also used this HD Kim's arc type bypass DTN, and we have plotted the mark contour. And the important performance parameters are these, out of which CF, CD are mainly focused. That is, CF is coefficient of force or thrust coefficient, and CD is discharge coefficient. So these are the results for DTN, that is dual throat nozzle without any secondary or primary injection. Same way we have for
Please wind up the presentation since only 2 minutes are left.
They wind up? I didn't get you.
Sir, only 2 minutes are left.
Okay. So this is the mark contours for VDTN. Similarly, we have contours for AVDTN, and this is for IDTN. IDTN is the DTN nozzle with injection without any bypass, and you can see the highest angle is achieved in this type of DTN nozzle. And this is the deflection angle curve for different nozzle pressure ratio for the 3 nozzles, that is DTN, DVDTN, and arc VDTN. And you can see that for bypass deck that is of V-shaped and arc-shaped, it is almost the same except for higher pressure. But this for IDTN, the deflections are very high. And also this plot for CD and CF, and as you can see, CD is almost same for, constant for 3 nozzles, and for DTN it is varying. And also for CF, all the CF values initially they are increasing, and after in higher nozzle pressure ratios they are decreasing. And this is what the highest deflection angle is achieved. The highest deflection angle achieved is 12 degrees, and that is for nozzle ratio of 6. That is for injection DTNs, and also it has the highest thrust coefficient. But as I mentioned earlier, and also it is from literature that DTN which injection has
Requesting
this
you
problem.
to stop the presentation. Now you can have the question answered.
All right. Any questions from anyone? No. Can I just check with you? Your simulations, is it I assume it's fully 3D. Is it your RAN simulation? Is it fully 3D or is it axisymmetric?
So sir, it is 3D, sir.
It's all fully 3D. So can you explain a bit? How do you get the vectoring? I don't quite understand where you get the vectoring from. How does the vectoring happen?
This test vectoring.
Yeah.
Actually, say for example, in this IDTN we have injection. We are injecting the secondary flow at the throat, so that the flow coming out of the nozzle gets deflected, and at the exit you get a flow that is deflected to a certain angle.
All right, thank you.
How much deflection angle you obtained?
Deflection angle is the highest deflection angle obtained is 12 degrees. That is for nozzle pressure ratio 6.
How did you estimate it?
We can estimate in two ways. We can do it with there are softwares for finding this, but still there are like we can get these pressure force values, that is the axial force versus the horizontal force, and we can divide it to get the theta values.
What is the advantage of dual thrust nozzle or dual throttle nozzle compared to SHTVC?
Compared to
SITVC, secondary injection thrust vector control.
Actually, dual throat nozzles, they are also coming under the secondary injection, but still BDTN, the advantage of BDTN is that it eliminates the starting problem that is mentioned in the literature, and also it has considerably high thrust efficiency.
Okay, thank you. Sir, anything else? Any other question from audience?
No. No. All right. Can you join me in thanking the speaker? Thank you.
Thank you.
The next paper ID is 95, titled as A Concise Explanation of Aerodynamic Lift and the Threshold Condition for Drag Divergence and Shockwave in Transonic Aircraft. Presented by Dekla Vinay, Professor Sanal Kumar, Ronak Sharma, Riya P. Day, Yash Raj, and Dhruv Panchal. I would like to call them on the stage.
Hello. Yeah. Thank you, Vedika, for your kind introduction. So, good afternoon, everyone. My name is Vinay. Today, I am going to present a very interesting topic called a concise explanation of aerodynamic lift and threshold condition of drag divergence. Introduction. As we all know that aircraft aerodynamic lift occurs when an object induces a change in the airflow's direction. Several factors influences the airflow direction, such as object shape, size, and its motion through air. So the generation of aerodynamic lift basically depend on mass and viscosity and compressibility effects. So the main objective of this research paper is to find out the common misconceptions in aerodynamic lift education and provide coherent explanation of aerodynamic lift. So basically, what is lift? How lift is generated? Which previously Bernoulli and Newton has explained using conservation of energy and momentum, but they missed out a very interesting topic called conservation of mass. So if we include conservation of mass into energy and momentum, so all conservation laws will be satisfied. So these explanations that they have given are not explained, not considered conclusive, but they only considered, as I said, energy and momentum. So in this paper, we are invoking Sunal flow choking, which was introduced by Dr. V.R. Sanal Kumar, who is here. So which encompasses the unification of conservation of mass, momentum, and energy, where all the conservation laws are satisfied. So as you see here, the aerodynamic lift was clearly explained by streamline compression. If you can see the streamline compression due to the flow turning. So due to upper curvature of the airfoil, flow gets compressed. So whenever there is a convergent section, subsonic flow tends to accelerate. That will create the flow acceleration and tunnel flow choking. So here external, the demonstration of stream tube flow choking. In previous presentation, one guy has done simulation of rocket nozzle where you can see the streamline compression. So this was published in Physics of Fluids 2022. So most of the people misconceived this incorrect theory of aerodynamic lift, that is equal transit theory. People says that you can see the point 1 P1 and P2. The flow from point 1 will reach at point 2 at equal time, but it is not correct. Due to its curvature, airfoil curvature, flow will be faster at the upper surface. So we should not misconceive this concept. And also Kutta-Joukowski, as you have heard, Kutta-Joukowski theorem, although it's a valuable concept, but due to its limitation, that he has used only inviscid theory. So all fluids are viscous in nature, as explained from second law of thermodynamics. So viscosity plays a crucial role in determining the flow behavior near these solid surface such as airfoils, where the phenomena like boundary layer separation and drag generation can occur. So here you can see, as I said earlier, streamline gets compressed, so flow gets accelerated, and it can reach Mach number 1 at a certain total to static pressure ratio that is given here. So the total to static pressure ratio is only depends on the gamma. Gamma is nothing but specific heat ratio. The specific heat ratio of air is 1.4. So the total to static pressure ratio reaches 1.89, you will get flow choking. So when a flow gets choked, if you add divergent section, it will get accelerated to supersonic. That leads to drag divergence. So at some point, it may lead to normal shock wave, which creates flow separation, and drag will be very high. That is undesirable. So consequently, aerodynamic lift is generated towards low pressure region of the solid object driven by momentum thrust, that is explained by Newton as well. But we are invoking all the conservation of mass, momentum, and energy together to explain the 100% lift. So these are the in silico demonstration of drag divergence. As you can see, 5 streamlines have been taken into action. So upper streamlines are getting choked due to acceleration. So when you see the pressure ratio corresponding to Mach number, at Mach number 1, the pressure ratio is 1.89. So it has accelerated to supersonic due to divergence, and again come to subsonic due to normal shock wave. So this threshold condition of drag divergence was explained in an analytical expression. So that is SFCI is nothing but stream tube flow choking index. So that completely depends on gamma, and there are multitude of parameters variates this condition. So finally, this review article presents a new perspective of aerodynamic lift, incorporating all the conservation of laws of nature. So Bernoulli equation is derived from conservation of energy. So Newton's law of motion pertain to conservation of momentum. So mass is an important parameter, as we all know. So we should invoke mass to complete the aerodynamic lift explanation. So tunnel flow choking is based on mass, momentum, and energy. So which satisfies all the conservation of laws. So if we use this condition, we can solve any real world flow systems. So we conclude that critical pressure ratio, that is SFCA, stream tube flow choking index, for choking serves a threshold condition of drag divergence. So in conclusion, so we are going to present that critical pressure ratio for tunnel flow choking resulting from stream tube compression acts as a threshold condition for drag divergence. To mitigate this, we suggest that injecting a fluid with high heat capacity ratio. So if we increase the gamma value, stream tube flow choking can never occur. So if you can see the equation, total to static pressure ratio is only depends on gamma. So when it reaches to 1.89, choking may occur. So what best we can do? We can increase the gamma by injecting a fluid which is having high heat capacity ratio. So knowledge of stream tube flow choking is crucial for improving performance and efficiency of vehicles like subsonic, transonic, and supersonic and hypersonic as well. So briefly, by considering all the conservation of laws of nature, this comprehension of aerodynamic lift offers valuable insights and optimizing and design of various aerospace vehicles, lending it credibility. So special acknowledgement to Professor Dr. V.R. Sanal Kumar, rocket scientist and lead member of the Indo-US investigators on asymptomatic stroke and acute heart failure due to flow choking. He has discovered this concept. So for introducing this groundbreaking concept to us for the design optimization of supersonic, hypersonic and re-entry vehicle. Thank you so much. So any questions?
Quantify the lift. How can you estimate the lift exactly using your code?
Sir?
Can you quantify the lift? Estimation of the lift using your in silico methodology.
Yes, till now there is no equation has come up. We know only one equation that is called L equal to half rho v square SCL. But we have to invoke the viscous effects in that so that we can quantify the lift.
So
any questions from the audience?
So do you have so can you predict the lift from your?
So it is the explanation of lift basically. So we invoked mass also so that all conservation laws are satisfied.
Any questions from the floor? No. All right, no questions. Let's thank the speaker for entertaining talk.
Next, I would like to invite paper ID 96. The title of the paper is Longitudinal Static and Dynamic Stability of a Biconic Re-entry Body in Subsonic Mach Number using CFD. It is presented by Jobin Benedict Leons, Jathaveda M. and Vidya G.
Okay, so good afternoon, everybody. The topic of my presentation is longitudinal static and dynamic stability of a biconic reentry body in subsonic Mach number using CFD. I have done it under my guides Chatveda sir and Vidya ma'am, who are scientists in ISRO. So this is the outline of my presentation. Introduction. Returning from the space is a critical task, which involves hitting the atmosphere at the precise flight path angle and velocity. It is necessary to dissipate the high kinetic energy, potential energy of the re-entry object. For our body, we have taken a non-propulsive ballistic vehicle, and stability is a very important aerodynamic parameter that should be taken into consideration for the trajectory design. The static stability parameters can be estimated either from the wind tunnel or CFD methods, whereas the dynamic stability primarily has been estimated from wind tunnel testing through forced oscillation, free oscillation, and aeroballistic range tests. So the steady state simulations have been done at Mach 0.6, and after that, dynamic stability has been tried to be estimated by forced oscillation technique in CFD. The scale of the model is inspired from a real life body, and the scale is of 1:10. This is the configuration of the body. The base diameter is taken as D. The model is a sphere cone flare configuration. The four parts of the body are the nose, the midsection, flare, and the base. The center of rotation is located near the end of the midsection. The body is oscillated about this point in the dynamic condition. The enclosure for the mesh is a cuboid, and the size is approximately 74D, where D is the reference length, the diameter of the body. Prism layers are generated from the surface of the configuration to capture the viscous flow physics. CFD simulations are carried out in CFD++ with the SST-K omega model. Steady state CFD simulations are carried out low angle of attack of alpha 0 and 2 degree for NAL wind conditions corresponding to Mach number 0.6. Post oscillation technique is employed for the same case with an amplitude of 2 degree. These are the solver equations that the solver is using, the Rance equations. And the turbulence modeling. For the turbulence modeling, I have used SST-K omega turbulence model. And the formulation of SST transport model combines the best of two worlds. It can be used as a low Reynolds number turbulence model without any extra damping functions due to the use of K omega formulation in the inner parts of the boundary layer, which makes the model directly usable all the way down to the wall through the viscous sublayer. The SST formulation also switches to K epsilon, and thereby the common K omega problem that the model is too sensitive at the inlet free stream turbulence is avoided. So the forced oscillation method, this is the method that is used in the dynamic condition. The method works by forcing the body to oscillate with a constant magnitude, and the simple harmonic motion method is one of the most simple displacement methods used in this forced oscillation method. There are three forms of motion in the simple harmonic motion: the plunging mode, the pitching mode, and the flapping mode. As we can see, there is the flapping mode, plunging, and the pitching mode. And these we have in our study, we have used the pitching mode to find out the dynamic derivatives, stability dynamic derivative, that is CMQ plus CM alpha dot for the dynamic case. The time step for the transient simulation is chosen so that it is good enough to capture the flow for the physics for 8 cycles. Steady state results are taken as the initial conditions for the transient simulation. So these are the equations that I have used. That is the angle of attack equation, the pitch rate equation, and these are the equations by which I have calculated the dynamic stability derivatives. So coming to the results, these are for the steady state condition. The residual plots, as you can see, it has converged. And we have also used the axial drag force showing convergence. This is the CP palette at Mach 0.6 for angle of attack of 2 degree. and mark pallet at the same mark at 2 degree. And we can see a large subsonic pocket with suction pressure in the wake region, a high pressure stagnation in region 1, and region 2, as we can see, has a leeward in the leeward side of the nose, indicates expansion and a drop in pressure. From the mark pallet, a decrease in mark number is seen at the stagnation point. Discontinuity in the mark number variation occurs at the cone junction due to the curvature change. A large region of low speed base flow is seen after the flare, which contributes to the base drag. So this is the normal force for angle of attack 0 and 2 degree. This is the cumulative normal force, the coefficient that is plotted, and the normal force contributed by each part of the body. The normal force increases from the nose to base, indicating that all parts of the body contribute towards the normal force coefficient. Both the midsection and the flare contribute equally to 75% of the total value. Nose contributes to 25% of the total. The contribution of the base to the normal force coefficient is insignificant, as expected. The plot for alpha 0 indicates that the normal force coefficient is 0, as expected. So this is the cumulative axial force coefficient, and for 0 degree and 2 degree both have merged, showing that the axial force coefficient is not very different. The nose cap contributes to 15% of the total axial force, followed by the similar contribution by midsection and the flare, 11% each. Base contribution is the highest at 63% due to the suction pressure due to the wake region that is produced behind the body. This is the cumulative pitching moment coefficient. The pitching moment coefficient for alpha 2 degree is negative, indicating pitch down, that is a restoring moment, and hence the body is stable in steady state. And these are the results that I have validated with the experimental condition. For drag force, I'm getting 13.81%. For normal force, 6.79%. And the XCP I have got in terms of D is 0.108 from the coefficient of, from the center of rotation. This is the dynamic stability force coefficient. These are the inner iteration time loops for the 8 cycles. This is the moment coefficient and the grid angle with respect to time. The grid is oscillating instead of the body. Hence, the positive amplitude of the theta would mean negative angle of attack of the body. The grid is oscillated with a sinusoidal motion, indicating the oscillatory pitching moment response. This is the CP palette for the body at the different instances, that is 1, 2, 3, and 4. Initially, the alpha is negative, which indicates the stagnation region getting shifted to the upper region of the body. Instance 1 and 4 are for 2 extreme conditions of the oscillation. This is the change of coefficient of drag and normal coefficient. I have also introduced the pressure probes, and these are the locations of the pressure probes and the variation with time. It can be noted that the pressure variations for the probes on the midsection and flare are in phase, and as they are on the same side of the body, they have increase in pressure. Base probe has no variation in pressure, probably because the point selected is in the center of the base. These are the results that I have got. The dynamic stability coefficient I have got as minus 0.39. The result is negative, which means that it is positive pitch damping, and has 16.32% difference from the test data, which is showing a good comparison. So these are the conclusion. Sorry. The longitudinal static stability and the dynamic stability for the typical reentry body was assessed at 0.6 mark. Steady state simulations were carried out at 0 and 2 degree on an unstructured grid of size 38 million to compute the static stability of the configuration. Any questions? Oh, one question.
Yeah, it was a great presentation. Have you considered heat flux? Because when a re-entry vehicle comes to subsonic, so it experiences large heat loads. So have you considered that in your case?
Actually, for our work, we have only considered the stability part of it. I have got the temperature plots and the temperature palettes, but I have not included them in the study. I have mainly focused on the stability point of view.
The stability when at Mach number 0.6, what was the initial condition you declared?
The initial condition was used for the steady state simulation at alpha 0 degree.
0 degree.
Yeah.
Have you considered running it 3D, unsteady runs?
Sorry?
Have you done any unsteady run simulations for this?
Yeah, this is a transient simulation. The dynamic condition I had used for like at a frequency of almost 15 hertz. So it's a transient simulation.
Yeah, but the unsteadiness is from the boundary conditions, right? Is that right?
No.
No. Okay, so any more questions from the floor? No. All right, if you could join me in thanking the speaker. Thank you.
We'll be having a tea break now, so I request everyone, all the students to proceed to F2 backside and all the delegates to proceed to F2 lounge. Yes. And please be here back in 15 minutes, that is 4:15.
One is converging a nozzle, which basically sonic sonic supersonic fluid, then it receives subsonic flow and produces supersonic at its.
Sir, you are on mute.
Yeah, my presentation is visible now.
Yes, sir, it's visible.
So I was discussing about nodules. So discussed about converging nodule, convergent divergent nodule. So coming to my topic, aerospike nodules. Here in the slide, you can see in the left side, we are having bell nodule, which is a type of basically convergent divergent nodule. So aerospike nodule is basically will be able to replace this bell nodule only because this is the inside out of the bell nodule. It's having a structure opposite to the bell nodule because here it goes out, but here it goes in. Okay, so there are two types of a spike aerospike nodules I have shown over here. One is that which is having full spike, and another one is that where we have we could basically truncate its spike. Okay, so along with this, other configurations are possible like annular types of nodule. Like here, the flows are basically annularly comes out from the combustion chamber, and another can be the linear one. So if we talk about aerospike nodule, these are the three figures I have added over here. Two are the cut sections, and the third one is that the full figure of the aerospike nodule. Here, this is the combustion chamber where we can have hot gases, and it goes out and then expands over here at the throat, and then expand to the atmosphere. So once it comes into the atmosphere, one side of the fluid is bounded by this spike, and another it is open to the atmosphere. Okay, so coming to the contour generation, how we will be able to generate the contour of this spike. So there are the various methods by using which we can generate the contour, like methods of characteristic, simple approximation method, Rouse method, Angelino method. Okay, so these are the methods which are available by using which we can generate the contour. In our case, I have used method of characteristic, which is one of the oldest method. Using the characteristic lines, which comes out at here at the throat, okay, and gives the points. So by just including all those points, we'll be able to get this contour here. Okay, so once we get this contour, we can generate the 2D spike or the 3D spike. To get the 2D spike, we can take the mirror image of this contour about this x-axis, or if we want to generate 3D contour, so we can just rotate this by 360 degree. Then we'll be able to get the 3D contour of the spike. So in our case, I have generated the contour by using the MATLAB code and then designed the domain. So for domain, here is the spike, here is the inlet, and these are the outlet, and this is the main domain. And we have also given the boundary conditions as well as namings. Okay, most of the places are defined in terms of pressures at the inlet, pressure at the outlet, okay, and pressure in the domain. So for the mazing of the geometry, we have used SMCFD. Okay, and then if we talk about far field, where the pressure, which are not basically affected because of the flow, what we are getting from the spike, we have taken 10 times of the length of the aerospike nodule. Here is the aerospike, and this is the far field point we have taken. So this is the mesh geometry, structured basically a mesh that we have created for the simulation. So for the simulation, we have used a Splat-Almaraz turbulence model, which are basically very good to give the spike bounded flow. In 2D cases, compressibility effect have been also considered over here in implicit formulation approach. Second order of wind scheme we have considered, or we have used basically, and current number we have taken 1, and then we have simulated over here. So this is one of the Mach number contour that we have generated by using the simulation. So if we talk about performance, so the performance parameters that we have taken over here are thrust along with the exit Mach number. So thrust is the main parameter. So if we talk about thrust, this aerospike nodule can give us thrust in 3 ways. One is that from the expansion of the gases here at the throat of the nodule, where the which is also called the primary nodule or the primary thrust, which is we are getting uh, because of the expansion of the gases. And the second type of thrust, which is called center body thrust, which we are getting from the spike. When the flows comes out and comes in contact with the spike one side, another one is that in the atmosphere. So this spike basically also develops or produces some amount of thrust. And the third type of thrust that we can get from this spike only, if we just cut out the spike, which is called truncation of the spike, so we can there are circulation of the flow basically occurs on the base of this spike. So it also produces third type of thrust, which is called base thrust. So these are the three types of thrust that we are getting. Thruster thrust, which is also called primary thrust. Second is that center body thrust, and third is the base thrust. So the total amount of thrust we can add all these three thrusts. So in our case, if we talk, we have taken fully spike nozzle, so base thrust will be 0. So we'll be having only two types of thrust from the primary nozzle and thrust from the center body. So a validation part here, for the reference, we have taken one of the published paper, and exit Mach number we have taken from the paper is 3.46. So for the same contour, for the same geometry, we have calculated it, it came around 3.4, where the error that we have got 1.734. As well as we have also calculated the thrust. So thrust from the reference paper, we have seen that 625.4 Newton. In our case, we have calculated
I would
and got
request you, sir, to wind up the presentation within 2 minutes.
Yes. I'm just concluding it. Similarly, we have also compared a nozzle pressure ratio. From the reference paper, we have got 187.5, and calculated value we have got 187. Similarly, if we calculate the numerical and analytical thrust, so it was coming error 0.003% only. So the validation part basically gives the full motivation, like we can use all those relations, whatever that we have done in our case. So in our case, if we talk about results and discussion, I have taken three cases. So over expansion, optimum expansion, and under expansion. So first we have defined the optimum expansion, where exit pressure is equal to the atmospheric pressure, and then based on that we have defined over expansion and under expansion. If we talk about over expansion, where the exit pressure, where the atmospheric pressure is basically more than the exit pressure, yes. So what happens over here is that when the gas flows out, outer atmospheric pressure basically compresses it and makes it convergent. So from this contour, we can see here that the flows are basically converging. Similarly, in optimum case, exit pressure is equal to the atmospheric pressure, though we are getting parallel type of flow. If we talk about under expansion, where at higher altitude, outer or the atmospheric pressure is less than the exit pressure, so the flows goes out. So we are saying that diverging type of flow. So based on these three altitude and then simulation result, we have calculated the thrust. For over expansion, we have seen 835, optimum expansion 5254.5 Newton, and under expansion 6248.7 Newton. So you see, from over expansion to optimum expansion, our thrust is increasing, and we go from optimum.
10 minutes are over.
Yes, I'm just concluding.
Okay,
and we go from optimum expansion to under expansion, our thrust is basically still increasing. But if we talk about bell type of nozzle, we go from optimum expansion to under expansion, thrust basically reduces. So this is the where that we are getting benefit of Aerospike nozzle. So because of the expansion to the atmosphere, at higher altitude, still we are getting more thrust as compared to the bell nozzle. So that's why we say altitude compensating nozzle. So I'm concluding my whole work. So I have basically generated the contour by using the method characteristic. By using the MATLAB code, we have got the geometry, and then meshing has been done in ICM CFD geometry. So based on the simulation result, we have calculated the thrust for all these different configurations, and then we have seen that if we increase the altitude, basically our thrust is basically increasing. So based on this, we can say that this is giving a very good result is an altitude compensating nozzle. So despite its drawbacks are like at very high temperature, the spikes won't be stand against this high temperature. Its structure may be changed. So if we just we will be able to solve this issue, so it will be very very a fruitful result will be available in the propulsion sector, and it will be very valuable asset in in propulsion we will be getting if we are using the Aerospike nozzle. Thank you. Yes, sir.
We would begin with the Q&A session.
Any questions from anyone?
The work is very good. And what is the biggest challenge in the aerospace nozzle implementation part in the space industry?
Yes, a main challenge is that because we are getting very high temperature gases, which is surrounding the spike, and this spike's structure is getting very very small if we go from base to the tip. So there is a chance that this will get damaged and it won't be stand against this very high temperature gases. So this very high temperature and pressure, this structure which is in middle of the nozzle, middle of the cylinder, just making it at this particular position, it is also very difficult. So the scientists are basically working, and we are also simulating some of the results so that we can just make it basically positive, so that we can just make this structure feasible.
Are you planning any static tests or verification with experiments?
So right now we are working on simulation part only. Still not didn't plan to go for the experimental one.
Any effort on truncation of the spike?
Yes, sir. We have worked on that, and we have found that around 46% of the truncation we are getting better result as compared to the full spike. But still, if we are just decreasing more this length of the spike, again this decreases the performance. So according to our result, we have found that at 46% of the truncation, basically it gives a good result. But again, it is also giving benefit of standing of this spike against this very high temperature. So this is one of the positive or feasibility that we are saying in the future that we can generate.
In your image, I have seen some exit flow is getting compressed. What is the actual cause of that compression?
Sorry, you're talking about that expansion of gases.
Yeah.
If we talk about this is occurring because of the expansion gases which expand to the atmosphere, and it gets reflect from there. It gets reflect from there and then enters into the domain again. So
okay.
Because of this pressure difference,
reflection,
that reflection, the pressure boundary from that atmospheric pressure boundary from there only.
Okay, then. Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Now I would like to call the paper ID 103. Are you there? Paper ID 103, Akshay Mohan. So we are not getting the response, so we are going to the next paper. The paper ID is 108. Paper title is Combined Effects of External and Nozzle Exit Flow on the Jet Acid Power Levels of Chevron Nozzles for Transonic Aircraft. The presenters are Arsalan Ahmed, Vinay Dekla, and okay. I would like to ask the presenters if they are ready with the presentation.
Thank you, sir. A very pleasant good evening to one and all present here. Today I, Mansi Srivastav, along with my co-authors, Sobia Raza and Tanisha Singh is here to present our paper on the topic Design Optimization of Chevron Nozzle in Transonic Aircrafts. Under our faculty guide, Dr. V.R. Sanal Kumar sir, here we'll be discussing about introduction, aim and objective, concept of Chevron, optimization of Chevron, simulation, results, and discussion. Aircraft noise is one of the most detrimental environmental effects of aviation. It is one of the most diffused environmental stressors affecting the modern life. As of May, as my personal experience, I live near Hindon Air Base. So I've experienced it many a times, like whenever the aircraft takes off or lands, it creates a lot of disturbance. So I can personally relate to this problem of noise pollution. The main source of noise pollution in aircraft is aerodynamic noise, noise from aircraft system and engine, mechanical noise. Among these, engine noise contribute most to the noise pollution. Then it can cause community annoyance, disrupt sleep, adversely affecting the academic performance of the students, and most precisely, it causes risk of cardiovascular disease in people. Like it is found that around every 5 decibel increase in every 24 hours can increase the risk about 34% in heart attacks, strokes, and other heart related problems. So that's why we came up with using Chevron nozzle instead of conventional nozzles. Basically, the aim, like here you can see we are using Chevron nozzles instead of conventional nozzle, base model, no Chevron, Chevron sharp edged. So basically our aim is to do aeroacoustic research and design optimization of Chevron nozzle for transonic aircraft. Chevron nozzles are sawtooth shaped nozzles which help in noise reduction. In fact, industries nowadays are using it. So we can do that with changing many parameters like changing the shape of the chevron, like we've done square shaped chevron, flat edged, and many other. Or we can change the height of the chevron, increasing height, decreasing height, and we can vary the space between the chevron and number of chevrons also. So, and one of the another we can use like maybe taper the chevron. Now over to you, Sobia. Thank you.
So it has been quite established that sound is a form of energy, and intense noise, such as those produced by aircraft engines, can have physical impacts on the human body. And going further in that, it can also have major impact in the blood flow and cardiovascular conditions. So that actually in a paper, in a groundbreaking study which was titled The Theoretical Prediction of Boundary Layer Blockage and External Flow Choking at Moving Aircraft in Ground Effects, which was published in 2021 in Physics of Fluids, discussed the phenomenon of external flow choking with relevance to the low wing aircraft at relatively high Mach number, which means that it is flying at very high speed, and at low angle of attack, which is the angle between the longitudinal axis of the blood of the aircraft as well as the incoming flow. This study is actually being included here because it can be correlated to the effect of the loud noise on cardiovascular conditions, which is striking. The thing here is that sonal flow choking happens whenever whenever fluid is flowing through a straight duct with a uniform cross sectional area, and the total static to pressure ratio reaches a critical value which is known as CPR, or critical pressure ratio.
The isentropic equation here states that whenever there is an increase in the total pressure ratio and there is a decrease in the static pressure, which can occur due to intense noise, choking occur. This slide is being showed here. It shows that how biofluid choking or the sonofluid choking can occur in arteries, and based on these, a unique condition for prohibiting asymptomatic aneurysm, hemorrhage, stroke, and symptomatic heart attack are being shown here. And for more clarification, you guys can infer this paper, which is actually in Physics of Fluids, published in 2021. Moving on. Actually, to optimize the chevron nozzle, there are different parameters which my teammate Mansi here has already explained about how it can be changed and adjusted to achieve maximum speed and maximum thrust with minimum noise. And based on the shapes, we have selected based on the parameter of the shape, we have selected different kinds of chevron. Here it is round edge. This is the geometry for the round edge, the square edge geometry, and the flat edge geometry. See, the thing here is that chevron nozzles actually disrupt the exhaust flow from the engines. And to achieve this noise reduction, there are several mechanisms which are being followed here. The first one is mixing and blunting of exhaust flow. The chevron nozzles have serrated edges and chevron-shaped lobes on their exhaust edges, and these serrations help in mixing or blunting of the high-velocity exhaust flow whenever it exists from an engine. And this abrupt flow in the flow direction caused by the serrations lead to the formation of a smaller vortices, which actually reduces the noise which are generated by the jet exhaust. Another thing is shock wave reduction. The serrations which are present on the chevron nozzles also help to disrupt the formation of the stronger shock waves, leading to quieter operation. The next thing is turbulent mixing. Chevron nozzles promote turbulent mixing of hot, high-velocity exhaust gases, which are exiting from the exhaust nozzles and with the surrounding cooler air. The mixing process here is more efficient than the smooth nozzle. That is, it is very different in chevron nozzle, and which results in more gradual transition from a high velocity jet to the surrounding air. As a result, the noise which is being generated by the turbulent flow is much lower. Other thing is that it actually modifies the frequency spectrum. See, the thing is that whenever these exhaust flow goes through these serrations, it breaks the noise into broader range of frequencies, which makes it less annoying for human ear and also actually reduces the perception of noise. Now we will discuss about the simulations.
So our team has performed simulations and in silico studies using a validated steady 3D density-based K-epsilon turbulence model. Our simulations take not only the internal but also the external flow around the nozzle into account. As you can see in the first simulation, there are no nozzles, and from the contour, it's clear that the flow that is going into the nozzle equals to the flow that is going out of the nozzle. And the Mach number over here is around 1.16, and the power acoustic level is 1.536 decibels. Now, in the second simulation, this is a chevron nozzle of flat edge. Here, just like my teammate Sovia told you guys, some of the thrust gets lost radially. Because of that, the Mach number over here is 1.07, and the power decibel acoustic level is 1.539 decibels. This is not a favorable result because even though the thrust loss is expected, but the power acoustic level has a slight increase. Then we have the last simulation of the round edge chevron. This one, just like the flat edge chevron, the thrust is lost radially, and we have a Mach number of 1.08. It's higher than the flat edge chevron, and the power acoustic level of around 1.503 decibels, which is the lowest of all the chevrons. Now, in the results, you can see that the round edge chevron gives us the most promising results. From the two graphs, the first one being the comparison of the Mach number, and the second one being the comparison of the power acoustic level, you can see that from the first one, even though the thrust is not being lost, compromised that much, from the second one, you can see that The pyroacoustic levels are mitigated the most in round-net chevron nozzle, which is what we had aimed to find out in the study. Finally, the round-edge chevron nozzle is the optimized nozzle, which reduces the pyroacoustic levels the most. Thank you.
Questions?
Hello. So several nozzles have been around for quite a while now, has been used in all the planes. What exactly was your analysis or optimization in the design of nozzles?
Over here, we have taken both the internal and external flows into account. Usually, people don't do that while studying chevron nozzles.
Sorry, can you do?
Our study includes both the internal and external flows around the chevron nozzle into account, which has not been done before.
Okay, thank you.
Any other question from the audience?
Can I ask, how do you predict the acoustic power level? Like, you're running a steady simulations, right? So how do you get the pressure fluctuations from?
We use a specialized KF7 model in ANSYS, which helps us, which is preferred for the pyroacoustic levels.
All right. Okay. Thank you.
Okay. What is your optimize your chevron in the future now?
Right now, sir, there's a lot of optimization that can be done in nozzles, including how many chevrons to be applied around the distance between the nozzles, if they are supposed to be tapered or not. So further studies are required for that.
You can propose your design to the industries to implement this chevron nozzle, because noise pollution create a health hazards. So what is your plan for the future in this regard?
We can taper the chevrons, like we can use the concept of expansion waves, and we can taper the chevron. And because when the using the chevron nozzle, that momentum thrust loss is there, so the industry is working over it so that to minimize the momentum thrust level. And of course, we are doing further studies upon it, and we will do.
Okay, okay, thank you. Thank you.
Okay, I have one more question. Noise is okay, but what about the stress concentration? Like you are using edges, and you are saying that there is an high temperature gases. What will be that?
Sir, I think we need further studies for that.
Like this is not actually
Okay, okay. So means you can take that as a future scope plan. Okay,
definitely more studies to be done.
okay, good. Carry on.
So suggestions well taken. Thank you for this.
The next paper ID is paper 116, titled as Recent Developments of Battle Tanks Used in Defense Applications, a Review, presented by Aditya Sadhu Khan, Srinivas, and Mahesha.
Yeah, good evening, everybody. Sir, this is not exactly falling under aerospace, the theme actually, but it's a part of that defense technology, and it's prepared by our one MTech student who is pursuing his industry internship. On his behalf, actually, I am standing before you to present the same. So it is a review paper that consists of some reviews of around 65 papers or so. Actually, he analyzed some 120 downloaded recent literature papers, but because of that page restriction and all that was posed by the organizers, we had to curtail it to around 65 papers or so. So this is the agenda that is there for the presentation. A brief introduction about the battle tanks that are used under the defense technology as a warhead also, followed by the classification and maybe the important factors that are considered during the design of the battle tanks as a matter of primary factors, followed by the advanced factors. And later, of course, what are the techniques that are being implemented in order to fetch all those factors that will be under consideration during the design of a battle tank. So with that conclusion, I think I am going to conclude the presentation that is prepared by the student Aditya. So the definition for the battle tank are numerous. However, some classical definitions will be running like this. It is basically a combat vehicle with enormous amount of fire power, mobility, impregnated with a protective armor, basically. So nowadays, of course, battle tanks, of course, 3 or 4 more factors are also, of course, combined together in order to make it a perfect weaponry. And the term battle tank was first introduced by the British during the World War I. And in fact, various forms of the Mark battle tanks, such as 1, 2, 3, 4, they were all used by the British in the First World War and in the Second World War to fight against the Germans. And there are numerous ways of classification of the tanks, of which only 2 are considered here. Basically, depending upon the weight and range of the vehicle, actually, or the battle tanks, they are classified basically as the light duty, medium duty, and heavy duty tanks. Normally, the light duty tanks, as the name itself indicates, they are small in size. However, gun power, protective armory that is provided, they all will be limited. Mobility, of course, is faster when compared to that of the heavy duty battle tanks. Of course, mediocre will be the medium duty battle tanks. And depending upon the generation of evolution of the battle tanks, they have been devised or classified into first, second, third, and fourth generation. Currently, of course, in the development is the fourth generation of the battle tank in order to meet up with a smart and advanced battlefield conditions. First generation battle tanks were in use till around 1960 and augmented with some night vision capabilities, night fighting capabilities, and NBC protection being armored. It turned into second generation, and usage of some alternative materials such as lightweight, equally competent materials such as composite materials gave rise to the third generation tanks. And a few classical examples that are classified for the various generation of the tanks have been put up there. So here is a picture of some of the battle tanks which were classified and were in use during the various world wars. It is Mark 1, 2, 3, 4, as well as various T tanks that were developed by the Soviet Union. So they have been classified under Mark 1, that is Tank 1, and that is World War II. And here is a glimpse of some of the views of the various, that is light duty and heavy duty types of battle tanks of the various countries with range. Maybe the overall, that is weight of the vehicle, GVW, that is gross vehicle weight of the vehicle in tons, followed by the range of the vehicle. So based on that, some of the popular tanks that have been used by various countries is in that is picture. Arjun, our own tank, followed by Israeli tank, and some of the tanks that were used by the France and Germany. So they are also being evidenced here. Yeah, some of the salient features of a battle tank are shown here. As many as around 20 to 25 parts can be categorized here, such as the optical image instruments, maybe the gun mantlet, main gun followed by the coaxial gun, various periscopes. Normally, the crew that will be allowed on every battle tank will be 3: commander, followed by the driver, and followed by the gunman. So here is a glimpse of the track system that is being provided along with the wheels, the idlers, and such track systems are normally the pillars of all these battle tanks when compared to the wheeled vehicle, because of which actually they claim several advantages. So these all are the various advantages of the battle tanks. Even though the large surface area is being taken over by the tracks, the moving elements here, however, the ground pressure exerted will be minimal and it will spread over the surface area, which will be maximum here, because of which, of course, damage that is caused to the surface terrain on which, of course, they will be flying will be minimal. And they are capable of pulling or pushing large loads when compared to the wheeled vehicles, and they can easily come across harsh operating conditions, terrains, trenches, and all these things. So these are the various advantages of the modern that is war tanks or the battle tanks. However, there are various disadvantages are also there, such as mechanical complexity, maintenance requirement will be more. Sometimes they may also may become immobile due to the track or link may be failure, or maybe spalling that may be taking place under the various types of terrains on which they will be flying, and such things, of course, need to be addressed when compared to the wheeled vehicles. And basic design criteria involved in every design, that is a design of the battle tank, involve three vertices of a triangle that is normally known as iron triangle basically. So that is nothing but the mobility followed by the firepower and the protection, that is the armor protection that is provided there. So the mobility, of course, involved in the battle tanks is further classified into three types of that is mobilities: transportability to the operational area, followed by the operational mobility in the operational area, and then, of course, the tactical mobility when in operation. So the firepower, of course, decides the ability of a tank to destroy normally the enemy tanks or the enemy armfare. And the protection, of course, is further divided into passive type of protection or the active type of protection that is armored normally to the battle tanks. So here is a glimpse of some of the performance parameters that will be considered during the design of every battle tank under each of the three vertices of that iron triangle also. The mobility is normally decided by the listed performance factors such as the maximum speed attainability, and engines which will be normally the diesel powered engines that will be used for the mobility of the tank and for the operational flexibility of the various equipment that will be there provided. Transmission system, suspension system, maybe the fuel consumption also matters, so that the range will be normally decided by that. Ground pressure and turning circle radius, so that maneuverability is normally decided by the turning circle radius. Smaller the turning circle radius, maybe sharpest of the turns also it can easily negotiate or maneuver. Similarly, firepower is guarded or decided by the various weaponaries that can be equipped onto the battle tank. Protection can be broadly classified into passive armor and active armor systems. Yeah, here is a glimpse of some of the that is mobility. So that is the first part of the design criteria that is considered while designing or devising normally the battle tanks. So they should be equally effective to transport to the operational area, maybe through terrain or sea or by air. So here is a glimpse of some of the types of transportability that can be normally that is provided during the design of the battle tanks. So operational mobility is actually the one which will happen during the operation that is involved under rough and harsh operating conditions. Yeah, tactical mobility, of course, decides normally when actually in contact with the enemies normally. And firepower, of course, can be that is equipped onto the battle tank is further divided into main armament, followed by the secondary armament, and some of the main armament that will be fitted on board the battle tanks have been listed there. Similarly, the secondary armament also varies, maybe depending upon the generation and class of the battle tank that is in use. And the survivability is one of the other inbuilt parameter that should be considered during the design of every battle tank. As many as 7 to 8 such that is layers, or maybe the survivability onion, we can simply call that as, is normally ensured during the build of every battle tank, where from exterior to interior, the interior is the one where, of course, the safety of the crew members that is involved there, and the various techniques that are used here for each of these that is safety protection layers are detected here. Suppose if the tanks, they are to be designed to not to be detected when in contact with the enemy. If they are detected, of course, various techniques such as the signature reduction technique, and if the tank is acquired by the enemies, of course, some jam techniques, jammers should be adopted. And suppose if it is then hit, so if condition is normally applied here, it should not be done in this way. However, if such conditions are prevailing to the tanks, these are the various techniques that are adopted by one or the other battle tanks in order to see that safety, utmost safety is ensured, not only to the systems equipped as well as the arms that will be there on board the tank, as well as to the crew members. So finally, of course, it will be the safety of the crew members that will be the utmost criteria, where some compartment techniques as well as some ERA grenades and such things, of course, will ensure that protection and such things are equipped to the this one battle tanks. So these are some of the chosen techniques, safety and techniques or armorage that are normally provided. Many of the Russian tanks, they were provided with a sloped armor as a passive protection technique. So where, of course, that for the same, of course, cross section, the thickness of the armor that was being fitted from the front or any side of the this one battle tank, that was enhanced there. Yeah. So these are some of the active that is armors that are being implemented all around normally surrounding the battle tanks in the form of ERA bricks, where some 3 layers of sandwiched that is explosive followed by 2 exterior layers of metals that are involved, so that whenever the tank is being hit normally by the enemy weaponry, normally, of course, the explosion here taking place will expand the explosive, and hence, of course, some protection will be given to the that is the main cage of the vehicle. And of course, the modern trend is to go for some more, maybe the criteria apart from the basic 3 criteria which have been that is defined previously, such as improved autonomy to the battlefield vehicle, adaptability under various conditions, and connectivity. So I will conclude here. And this is the process flow chart that is being followed during the design of every battle tank normally, which involves normally the study of the open domain source that is matter that is available, material available, followed by the selection of the suitable material, and testing of the material, both that is destructive and non-destructive, followed by the model preparation, simulation, and analysis, and fixing of the suitable manufacturing process, and then, of course, some inspection during the manufacturing, followed by after the manufacturing will be carried out. And these are the primary alternative materials that are in use as a armorage normally. So the initially the good old material has been the RHA, which is steel based material, which is now taken over by the various alternative materials such as composite materials, aluminum, and maybe titanium based materials. They are taking over nowadays in the modern that is battle tanks. And these are the concluding remarks, that is survivability, firepower, mobility, and others, command, control, and crew comfort are the main criteria that are considered during the design of any that is battle tank. And vibration and oscillations of the gun barrel can be eliminated normally by reducing the mass. So, and maybe the detonation delay, standoff distance, variation of the angle of impact determines normally the overall effectiveness of the ERA, that is explosive reactive armors. Thank you.
Questions? Any questions? No, nothing. All right. Join me in thanking the speaker. Thank you.
Thank you so much, sir. Now I would like to invite the paper ID 104. The paper title is Analysis of Indian Aircraft Maintenance Engineer Licensing in Global Regulatory Framework. The presenters are Manoj K, Dr. Sanal Kumar VR, Dr. Sanjay Singh, and Deepak Chandra. I would like to ask the presenter if they are ready with the presentation.
A very good evening to the aviation experts and the aviation enthusiasts. Till now, we have seen all the technological perspective. Now we will look in the direction of the regulatory perspective. This paper belongs to the regulatory perspective, and I'm going to discuss about the analysis of the aircraft maintenance engineer license in the global regulatory framework. Let us see how it flows on. Just So this clearly reflects how the regulation is required in order to ensure, the proper compliance. So in my presentation, we will be discussing about how the International Civil Aviation Organization states about the personal licensing when we are handling the aircraft maintenance for the engineers. Here I have considered, of course, in the entire world, there are quite a few regulatory bodies. I have selected a very few. The primary one is the International Civil Aviation Organization, the DGCA, India, the EASA, European Union Aviation Safety Agency, and one more is that we will just discuss ahead. In this presentation, we will be going ahead in the regulatory requirements, the research paper, the methodology, how we have analyzed how we have analyzed the papers, and we have did the comparative analysis of the various regulations, and also the expert interviews were summarized in this particular paper. And based on this analysis, we have brought out the various areas where the scope of improvement is required, and the important thing, how the careers is going to grow when we have harmonization in between the various regulatory bodies with regards to the licensing part, and what are the limitations I have come across, and what are the limitations of this paper, and how the future scope of research can go ahead. That is what is the discussion about. And the objective is to increase the acceptance of Indian AME licenses internationally, and the scope of this particular paper is limited to the analysis of regulations, training process of AMEs in India, of the prominent countries too. So the regulatory bodies which I have considered for this particular study is the Annexure 1 of the International Civil Aviation Organization, which precisely talks about the personal licensing part, and aircraft maintenance engineers licensing is a part of this particular annexure. And EASA Part 66, CAR 66 of DGCA, CFR Part 65 of FAA, CAR Part 2 of GCAA. These all regulatory bodies, and this particular precise part talks precisely about the aircraft maintenance engineering licensing requirements. So in line to that, I have referred quite a few research papers. Some of them are as stated in the slides. The methodology of the research for this particular paper is mixed methodology was adopted. The survey was conducted with the expert interview survey was done. Comparative analysis was done with the various regulatory bodies. Comprehensive literature review is done, and the documentary analysis precisely talks about what does the individual regulatory documents are stating about, and what are the differences, what are the commonalities, and how we can harmonize between among those regulatory requirements is what the analysis actually done in this particular paper. So the expert interviews were conducted with the engineers who are having more than one license. What I mean exactly by more than one license is there are few engineers, they have the license from various regulatory bodies. So we have filtered out only those experts who are having more than one license, and we have taken their opinion based on the open-ended questions. With the help of the comparative study, we have found that the age requirement for obtaining or for even applying for the license is 18 years of age. In addition to that, the engineer is required to, or the prospective engineer is required to have language proficiency, academic qualifications, and training organization approvals. And in order to assess the knowledge of the particular candidate, the various tests with regards to the aviation law and aviation maintenance and engineering are very much required. As such, being an engineer, it is not required for us to learn about the aviation law. But when a engineer or a prospective engineer performs the maintenance on the aircraft, he is binded by the regulations of that particular country where he is being issued with the license. He is binded by the law of aviation. He cannot, supersede or cannot, violate any regulations which are stipulated under the license which he is binded upon. And when we have verified the experience requirements of the particular engineer, the International Civil Aviation Organization stipulates 4 years of experience is required in the aviation industry prior he obtains the license issued by any of the regulatory bodies which are under the umbrella of ICAO. Most of them are. But when we are talking about how these various regulatory bodies and how the engineers are facing the challenges when they go to other countries or other regulatory bodies to perform their or to utilize their license in other nations, it has been brought out by the expert interviews that there has been and there is a various tremendous growth in the aviation industry which requires qualified and skilled engineers. And there is a challenge in the difference in training and certification processes of the various regulatory bodies. That itself is also a minor hurdle between the engineers to go from one regulatory body to the other regulatory body controlled nation. It is also highlighted that various regulatory bodies, even though they are under the umbrella of International Civil Aviation Organization, they are limiting the acceptance of other nationals or the licenses issued by the other regulatory bodies. So we, in this particular paper, we have found out that how we can strengthen and how we can reduce the gap, what could be the proposals, and how we can make really a global village, excuse me, really a global village with regards to the aviation industry. The most of the experts have stated that harmonization with the EASA and international regulations will enhance further acceptance rate between various regulatory bodies with regards to the aircraft maintenance engineer licenses. But however, the scope of training organizations and few regulatory bodies are not focusing on the duty time limits of the aircraft maintenance engineers. These are quite a few challenges which the experts are stating upon, are brought out. So how we can improve it? The scope of the improvement is between when we create the harmonization among the various regulatory bodies requirements. Even though they are under the umbrella of International Civil Aviation Organization, still the regulatory bodies are having their own independent requirements. Like FAA is having a peculiar training requirements. EASA has stipulated various acceptance of the type training schools. The candidate who has undergone the AME course under an DGCA approved organization, his experience requirements are different than the engineer who directly applies for the license based on clearing all the examinations and the requirements. In addition to that, it is very much important for us, and in any field of professional employment or in a business environment, soft skills are very much important, and the recurrent or the continuing of the education is very important. And they were also brought out in this particular research and the study. Soft skills and the continuing education in the aircraft maintenance engineers is also playing a vital role in causing as a hurdle for the acceptance rate among the various regulatory bodies. How this can enhance the career prospects? After COVID-19 and due to the economic slowdown, the aviation industry has severely impacted. This has caused quite a big challenge for the aircraft maintenance engineers. However, now we are seeing a tremendous growth in the aviation industry, and it has been brought out by IATA. Within next 20 years, the requirement of the aircrafts are double the existing ones. And the biggest aircraft manufacturers are saying that they will not be able to meet the requirement in the next 15 years also, as per the present demand we are having. Not only in the aircraft maintenance core for the maintenance, and the upcoming the UAVs or advanced technologies, IoTs, everywhere these particular new technologies are required to be implemented in the aviation industry also. They cannot be brought out directly a guy who is a software engineer. The experts in the aviation industry are required to be associated there. Then only they will be able to understand the problem and able to address it in a rightful way. Due to this particular growth in the IT sector also, the growth and the career possibilities for the aircraft maintenance engineers also will shine. As I have already said, that industry is growing tremendously well, and I'm sure if we are able to harmonize, as we have discussed in the paper, we will be able to make sure that the engineers get their better career opportunities than the existing ones. That's all from my side. I'm ready for the question.
Any questions?
So what is your future plan for this licensing?
Sir, this particular paper we have already discussed in as such for everyone. I am a deputy director in DGCA, Director General of Civil Aviation India. So I have already brought these particular points out in my own office, sir. So it is being considered for discussions with the various regulatory bodies in the common platform whenever it arises. And that's what as of now, sir. And we are looking forward for a meeting with them.
What is the time frame for implementing the new licensing procedure? Because safety is the major concern.
Yes, sir. Sir, of course, I can promise with regards to the India side, but I cannot promise with regards to the international regulatory bodies. But I believe this is a very convincing point what I have stated, and I'm sure everybody is intelligent enough to understand and how we can make the industry shine. I'm looking forward for a positive note from the other regulatory bodies too.
Okay, thank you.
Is Australia participated in it?
I yet to know, sir. This is not a plan yet. It is
all countries should participate because
yeah,
it's a airline. It's a global industry.
Yes, of course, it is going to be.
All right, thank you. Thanks for your presentation. That's.
Thank you.
Thank you all for actively participating and contributing to this insightful technical session. Your engagement and enthusiasm have made this event a grand success. I wish you have yourself a great evening ahead.
So we have this dinner, okay, only for secondary delegates and few our students. We have a more at 7:50. You are here?